Thank you very much. Good morning, everyone. First of all, I want to thank Dr. Sandeepan for this invitation, this wonderful opportunity. It's always great to visit IIT Hyderabad because it's like coming to a different world. The campus is so beautiful. Apparently, every building is designed to look different, distinct. And every time I visit, there's something new coming up, and the garden is coming up so beautifully. So today I'll be talking about some work we are doing in the field of networks of oscillators. Right, this is an AI conference, and you all know about AI and deep networks and all that stuff. As you know, deep networks were originally inspired by the brain. So way back in the 40s, when McCullough and Pitts were trying to understand how brain works, they started with how a neuron works, single neuron. So proposed that it works like a logic gate, and then therefore brain is like a Boolean network and works like a computer and all that. But that idea quickly ran into rough weather because brain is not like a computer, it trains by itself. So in the 60s, Frank Rosenblatt said, no, we should come up with a training algorithm. And he proposed the perceptron algorithm. This is all very old history. Some of you might not even have heard of this. So that went on, and in the 80s, algorithms to train larger networks, what are called multi-layer perceptrons. Now we call them deep networks. These things were all developed in the 90s. Really, they were hyped up, and a lot of work has happened. In the 2000, deep networks were rebranded. The MLPs were rebranded as deep networks, and it went on from strength to strength. And you have this whole wonderful field of AI now. That was the history behind this whole field. But although the original inspiration has come from brain, if you poke into a deep network and measured how the neurons behave, what is the responses like, it won't look anything like what you see in the real brain. Because if you give a human subject an MNIST data, right, a picture of 6 or something like that, and okay, the person recognizes it, and then you poke into the brain and see how the neurons are responding, what is their activity like, it doesn't look anything like what you see in a deep network. Right, then where is this inspiration, biological or neural inspiration gone, right? What did we do with it? So because in the brain, if you measure anywhere, you'll see oscillation. You'll see oscillator activity. Even when you are sitting quietly doing nothing, there's a lot of oscillations going on. Whereas in a deep network, there are no oscillations. Even if you take an RNN, there is no oscillation of the kind that you see in the brain. So is it important, right, to design, is it important to copy brain as it is and reproduce all these features, or is it just unnecessary, distraction? Okay, we believe that it is important to capture this oscillatory activity, which means you need to create a whole oscillatory neural networks. So I believe I believe that this kind of networks what we're proposing in this talk can act like a convenient bridge between computational neuroscience models and the artificial AI models. There's a big talk going on, the buzz in Silicon Valley now is, how do you bring neuroscience and AI closer? Because inspiration has originally come from brain, but somehow we lost the way and stopped looking at the brain. Now we need to go back and look at the brain and bring these two fields closer. How do you do it? So I think a bridge between these two fields. This is what my starting point is. So my lab, CompNeuro Lab, our big goal is to build a model of the whole brain, right? And once we do that, I think it will have immense applications both in medicine, that is neuroscience, neurology, and engineering. So for that, there are huge brain processes going on in the world, but we are talking about slightly simplified brain model, a cartoon model, which we call the meso brain. The meso is middle, right? So in this model, in this hypothetical model, there's sensory inputs, there's motor outputs. Between the two, you have the prefrontal areas, of where you do decisions. And then the 3 parallel loops, the cerebellum, basal ganglia, and hippocampus. So if you do this, I think you have got essentially what a mammalian brain is like, and after that it's detailed. It's not as simple as what I'm trying to make it out, but that's a very good starting point to understand brain at a large scale. So to that end, we have been working on different pieces of this big picture. We have done a lot of work on basal ganglia, some on hippocampus and spatial navigation, some vision, some eye movements, and so different parts. We are trying to assemble all these pieces, hopefully before I retire. That's a joke, right? We hope to build this whole brain model. To that end, I divide the lab into different teams. Each team works on one focused problem. So now I'm going to talk about the work of one of the teams, which is neural oscillators team. And okay, so if you know about neurons, right? If you record from a neuron anywhere, you will see activity that goes something like this. You'll see voltage fluctuations, right? Which go anywhere from like -70 to about 20-30 millivolts. And you see very sharp voltage spikes that are about 1 millisecond long. Now the question is if you tap into any computer bus in a computer, right, a wire, you will see the digital signals going from some 0 to 5 volts, whatever. So similarly, so you know that that's the binary information. low voltage is 0 and high voltage is 1. That's a code in the electrical signal. Similarly, in the neuron, what is a code? If you record these voltage activities, what is the information present in it? That's a big question. So there are two schools of thought about it. One school of thought says, look, these spikes, these are action potentials, these are called also loosely called spikes. The actual spike shape is pretty standard. Spike height and all that is very standard. It's almost like an atom. Therefore, the only information present is the time at which the spike has occurred. So you can approximate this by a series of delta functions. So that is one school of thought. This is called a spike code. The other theory says, no, you don't even need that kind of a detail. Just look at the average frequency of the spikes, and that's called the rate of firing. So so if you have a series of spikes like this, high frequency here, low frequency here, so it just represented by a line, by a graph like this. That's called the rate code. So there are neuron models which are based on the idea of spikes. They are called spiking neuron models. The neuron models are based on rate idea. These are called rate coded neuron models. So in AI, what you actually deal with is rate coded neurons. You never look at spiking neurons. There are also deep networks of spiking neurons, and these are called neuromorphic engineering, and that's a whole different field. So you have ReLU and sigmoid, and if you want to have memory and dynamics and all that, you use some kind of LSTM or GRU and things like that. And then with that, you construct large networks, deep networks. You know all this story. Similarly, on the other side, in the other camp, also you have interesting neuron models which capture the spike activity. The simplest of them is what is called leaky integrate and fire neuron model. How many of you have heard of this, leaky integrate and fire? Okay, so we are now looking at the other camp, right? So that's a very simple neuron model with one differential equation. That's the simplest you can think of. It's actually a pretty bad model, but I mean that's the simplest. If you want to really simplify it, you'll get something like that. Then there is this very beautiful class of models called Izikevich neuron models, which two variables. And just with two variables, you can get immense variety of spiking activity of real neurons. Because the thing is, brain is very rich. Biology is very flamboyant, right? It likes to show off. There's immense complexity and variability, diversity at every point in the brain. If you go to subcell, inside cell, it's like a whole city. So I have no wonder, if a single neurons also behave, every neuron has its own song, and so when you model it, it becomes a challenge. This model captures a wide diversity of neuron firing patterns. I'll show you some pictures very soon. Then you have Hodgkin-Huxley model, which was proposed in the 60s. This was practically the first computational neuroscience model. It's a model of a real neuron, how it produces these spikes, how the ion concentrations, ionic fluxes in the neuron produce all this voltage activity. And they got a Nobel Prize for that. That was the first major model. And then you can have even more detailed models. Okay, so let me just give you a flavor of this. A leaky integrate and fire neuron model is basically a RC circuit. We all know what is R, what is C, resistor, capacitor, and all that. RC circuit, you inject some current into it. So capacitor gets charged, keeps getting charged up. Once the voltage crosses some threshold, you reset the voltage. Just dump all that voltage into the ground. Again, the charging continues. Okay, so the voltage builds up like this exponentially. Once it reaches threshold, reset. Build up, reset. This is how the neuron behaves. The idea is that whenever that resetting happens, imagine there is a notional spike generated by the model. So this is a spike neuron model. So depending upon the current fluctuation in the input, right, your spike pattern also will keep changing. This is a leaky integrate and fire neuron model. Now, Izikevich is I'm such a fan of this guy's work. He's written a beautiful textbook called Dynamical Systems in Neuroscience or something like that. So because one of the problems in the brain modeling is you don't find many deep theories. You don't find, like in engineering, if you take any field, you have some fundamental laws, and everything is constructed out of the fundamental laws. Whereas in biology, everything is different. Oh, this is cerebellum. Oh, this is basal ganglia. So that's diversity is just diversity. Very often you don't find those unifying laws. So whereas this is very exception, this work is exception. Just two differential equations. One of them has quadratic nonlinearity, second is linear. And just by varying four parameters, A, B, C, D parameters, you can produce all these different kinds of firing patterns. Each of them has a name, and these firing patterns are actually seen in real neurons. Okay, so it's amazing how he was able to formulate such equations. This is the Hodgkin-Huxley model, very complicated, 4 variables, highly nonlinear. But this is the first model proposed, and people have simplified it later and so on and so forth. And they got Nobel Prize in '63. Now, more recently, what people are doing is you have so much data available at single neuron level, subcellular level, that given a neuron, suppose I pull out some bipolar neuron from my retina, right? I can know, okay, what is the cell size, what is the wire length, how many branches are there, what is the conductance of different segments of this wire, and what kind of neurochemicals it is generating. I mean, everything, right? I mean, it's actually too much of data. A plethora of data is available. So what they do to model a neuron, single neuron like that, is chop it up into small pieces like this, and each piece is modeled by a circuit. And it is similar to a huge circuit for a single neuron. You see, just because you have data, lot of data, but if you keep modeling single neurons like that, say if a single neuron has 500 compartments, 500 pieces, and it will take a very high-end computer to simulate single neuron. How are you going to simulate large networks? How are you going to simulate large parts of the brain to understand pathology? Somebody wants to understand, let us say, some glioma, right, some brain cancer. You'll have to simulate, millions of neurons. How will you simulate millions of neurons if single neuron is so complicated? So this is a big problem. So not $1 billion, because I'm not using dollar these days. Dollar is crashing, I believe, right? So let us call it like a 1 lakh crore problem, rupee problem. Is you have these two extremes of neuron models. On one hand, you have this compartment models, whereas for a single neuron, I'll need like some 1,000 differential equations. On the other extreme, you have this very abstract neuron model called Makalo and Relu and all that, which is biology is all thrown out. It's too artificial, but it's very good at network level because it's literally changing human civilization, right? The AI and all that. So that is two extremes. Is there a midpoint, a golden mean, where we should operate? Then if you operate at a midpoint and develop network models, that will look like brain models and illumine what happens in the brain on one side, and also will have very powerful artificial AI applications. This is what we are seeking. This is a midpoint. So where is that midpoint? So one answer we can, here we can take inspiration from engineering, which is, if an aeronautical engineer is trying to design some aircraft wing, they won't try to follow the molecular collisions on the wing and all that. That's stupid. I mean, that's very impractical. We invoke something called a fluid, and fluid is an abstraction. A fluid element is like, has billions and billions of molecules, all treated as one lumped element, right? And so you study the flow of fluid using Navier-Stokes equation, and you are able to design this very well. So question is, why can't we do the same thing in neuroscience? So instead of looking at single neuron activity, just look at activity of a whole mass of neurons. In fact, there are such models called neural mass models. So how do they work? Instead of recording from single neuron, just shove a blunt electrode in a whole neighborhood of neurons, maybe some 10,000 neurons. Take average activity of that whole, what's called a neural ensemble, a group of neurons, and record that signal. It's like recording what's happening in this room by just simply putting a microphone at the door. It will give some average activity of what everybody is saying, right? And that signal, you low pass filter it, you kill all these sharp spikes and all that. You get a signal like this. This kind of signal is easy to handle because if you have delta functions, it's difficult. The equations become very painful. But if you have smooth signal like this, you can use all your signal processing methods. You can use oscillators, right, to model them, to construct them, and so on. So now so let us now start with this hypothesis. Let us look at average activity of a whole set of neurons, and then build computational models to describe networks of such units. How does it work, right? So now, oscillator activity is very common in the brain. There's a huge literature talking about them. So brain frequency band is actually very small compared to the frequencies of your communication system. Here you talk about gigahertz and all. The frequency is different. Yeah. So you divide the whole, so like, instead of gigahertz in the brain, you only have from 0.1 hertz to a couple of 100 hertz. That's all. It's a very small band. Within that small band, people have divided into subbands. So 0.2 to 3 hertz is called delta. 3 to 8 hertz is called theta, and so on and so forth. So alpha is what you see when you are sitting in a quiet meditative mode with eyes closed. Beta is what you see when you're thinking, and gamma is even higher, and so on and so forth. So people have given some interpretation to each of the frequencies. But the problem is there is no good deep theoretical framework to describe how all this is happening. I'll come back to these issues later towards the end of the talk. So we're talking about the midpoint, right? What is that midpoint? So it looks like that midpoint is, if you describe brain activity in terms of oscillatory activity of these huge masses of neurons. So if I take a single oscillator, it's clear, you know, amplitude, phase, and frequency. If you have a more complex signal like this, so here you have a clearly an amplitude idea. When you have a narrow band, you have a clear definition of what an amplitude. In that band, that's the whole amplitude. So here in this paper, Bazaki and Dragun published in Science, they are saying that the middle ground is the oscillating networks is now viewed as the critical middle ground linking single neuron activity to behavior. Right? Single neuron is much smaller than this mass of neurons. Behavior is what you see outside. What links the two is this networks of oscillating masses of neurons and their synchronization between them. You can connect these two using such networks. So I'm basically motivating why should we study oscillating networks from neuroscience point of view, because your brain has it, so you put it into your models. That's what I'm motivating. But oscillators are getting a motivation from a very different angle of late, right? Especially last 6-7 years. There's a paper by Saba and Porod, 2019. What they're saying is it is very good to study oscillator networks, circuit models, because they're very energy efficient. Take the simplest oscillator, LC circuit, inductor and capacitor, right? Put some energy into it. It'll keep oscillating forever without any loss of energy, if it's ideal, right? So way back in the 50s, John von Neumann, who's father of modern computing, he thought that in computer hardware, right, how do you represent binary information? Now we represent 0 as low voltage and 1 as high voltage. But what he suggested is take two oscillators, look at their phase difference. If the phase difference is 0, call it binary information 0. If phase difference is pi, call it 1. So if you represent like that, then since oscillators are energy efficient in their hardware implementations, the computing technology will be more energy efficient. And he even has a patent on that in the 54 or something. But for some reason, computer technology didn't develop in that direction. We are left with, you know, this digital idea and 0 low voltage, high voltage and all that, which is very energy inefficient. Because a brain, human brain, the wattage is about 40 to 50 watts. I mean, like a normal light bulb. I mean, imagine an AI machine with its cooling, you know, systems and all that stuff, right? People have to have separate power system just to, you know, power this thing. So, what is the secret of the brain's energy efficiency? Because it deals with oscillation, is that where the secret is? So that is the angle from which there's a renewed interest in looking at oscillatory models, not just for its computational properties, but also in its hardware realizations, its low power angle, right? It's low power significance. That's what is motivating people now. Okay, so the oscillator models, neuron models are there. We don't have to create them afresh. For example, there is the Wilson-Cowan model, very familiar neuron model. Just two differential equations, nonlinear. Then Fujii-Nagumo is actually systematically reduced from Hodgkin-Huxley model. The Morris-Lecar model, which is actually a model of a muscle, not really a neuron. Again, it will produce oscillations. Van der Pol oscillator, anybody has heard of Van der Pol oscillator? People use it even in mechanical engineering to model vibrations, to model cell cycle, to model cardiac oscillation. I mean, everywhere people just use it left and right. It's a very simple nonlinear oscillator model. Okay, so we can think of this kind of a oscillator as a model of this, what is called low local field potential, this gross, you know, combined oscillation of a large number of neurons. But the thing is, this kind of oscillation is different from the kind of oscillatory equation that you might have seen in your high school. Right? How many of you heard of simple harmonic oscillator? Yeah, so pendulum, right? Now pendulum equations will be like what? D square x by dt square plus omega square x is equal to 0. But this is different from the kind of oscillation we are looking at in the brain, because in case of a simple pendulum, if I start with a small initial amplitude, that continues. It will keep oscillating at low amplitude. If I pull further away and let it go, it will oscillate at higher amplitude. So in this plot, which is a plot of position and velocity, if you start closer to the origin, you will keep going around in a smaller loop. If you start further away, you will go in a larger loop. It is a loop, it is periodic. But thing is, the amplitude of the oscillation depends on the initial condition. Whereas neural oscillations are not like that. There's something strange about them. So if I have an oscillation like this, a neuron's output, if I give it a pulse and disturb it, there's a transient increase in voltage or variation in voltage, but after some time it will settle down to the same amplitude. It will always oscillate at a standard amplitude. That's a kind of neural oscillation that you see. But whereas your SHM doesn't behave like that. So you need different equations. So that kind of a mathematical oscillator model is called a limit cycle oscillator. So very different from your simple harmonic oscillator. And that has to be a nonlinear model. You cannot, SHM won't work. So what is a limit cycle? It's a closed loop. The activity tends asymptotically towards a closed loop. So if you start anywhere in this plane, it will go back to that loop and keep oscillating in that. Usually they're studied in a plane, but in principle you can have it in any dimension. Higher dimension you can have this kind of oscillations. So how do you produce them? What kind of mathematical model produces them? Any questions so far? The simplest kind of equation you can produce is this, what's called a Hopf oscillator. It also goes by different names, but you can call it Hopf oscillator. So it is two variables, x and y. In fact, this part is nonlinear. If you ignore this part, what is left is actually, this part is just simple harmonic oscillator. So take simple harmonic oscillator, add some nonlinear terms to it, you will get this Hopf oscillator. So it looks kind of scary because cubic nonlinearity on the right side and kind of looks very scary to analyze. But actually it's only an appearance. If you transform the variables from Cartesian coordinates to polar coordinates, r theta, by making this substitution, these two will collapse into something so simple, like ridiculously simple. Right, this is for r dynamics, this is for theta dynamics. The theta dynamics is very simple. Theta dot is equal to some constant, means it will just keep going round and round. R dot is equal to this. What's going on here? If r is less than 1, let us say, this part is positive, which means r dot is positive, which means r increases. If r is greater than 1, this part is negative, so r decreases. So what is happening here? In r theta coordinates, theta simply goes round and round. R, no matter what is the initial value, it goes to 1, which means in this picture, no matter where you start in the plane, you'll always go to the unit circle, keep going round and round. That's the limit cycle. Right? Going always to the fixed amplitude oscillation is a limit cycle behavior. So it's a very convenient model of the simplest model of a limit cycle. The beauty of this particular set of equations is that you can easily write them in complex form, complex domain. Why complex domain? I mean, already it's such a painful thing, and why are you bringing in complex algebra and all that? The thing is, it's interesting that when you describe these oscillations in complex domain, you get very beautiful theory at network level. Right? You won't get this if you write in real terms. Right? And then and also it's not coincidental that how many of you are electrical engineers by your basic training? Electrical engineering is all complex algebra. Systems theory, transfer function, Fourier transform, they are all complex, right, concepts, right? Somehow, the moment you talk about oscillations and signal processing and systems, you end up with some complex formulation. It's not surprising that we also kind of went in that direction. It is just that this is for nonlinear systems and networks. Okay, it's probably just a nice coincidence, okay. So you can write the same thing in complex terms like that. And you can easily show that this and this are both the same because you make the substitution, z is equal to r e power I theta. Do the substitution, you get the same equation. So just for verification. Okay. So now let us take this as my basic computation unit, this oscillator, and then construct networks and see how they behave. Okay. Now our big agenda is, so you know the neural network theory, right? You can have MLPs, which is basically deep networks. You can have autoencoders. You can have self-organizing math. I mean, the whole spectrum of neural network models. Our goal is to reconstruct the whole thing using this kind of complex oscillators. Okay, we have done it. We finished that exercise. This was, my slides are slightly old, so it says done, this is not done, but everything is done. I'll show you one by one all these things. Let's start with a single oscillator. Let's study their behavior. If you look at a single neuron model, what's the first thing you look at? Its activation function. Is it a sigmoid? Is it a ReLU? Right? So for an oscillator, what is the activation function? When you present an oscillatory input, a periodic input, how does it vary as a function of some input, which is typically, frequency is the most important part of, as property of the input. As a very input frequency, how does the response amplitude change? Any oscillator is expected to have some kind of a resonance property. So if I give a complex sinusoid input to this oscillator, and when the oscillator input and the oscillator and the inputs of frequency match, it should give you a high response amplitude. You see that here. Hopf oscillator does show resonance. The x-axis is the frequency difference between the oscillator frequency and the input frequency. When the difference is 0, you get high amplitude. When you deviate from that 0, you will get this. So you get some kind of bell curve. So this is the first thing we want to note. This was studied in chem and large. We didn't do it, and it's already there. This theory is already there. Okay, now let's connect oscillators to construct networks. The simplest network will have two oscillators, two units, so couple them. Couple them in a back and forth fashion like this. Let's see what happens. So I have two connections, W12, W21. Let's see what happens. I'll take two cases. W12, W21 are both the same, so I'll take symmetric connections, and both are positive, some 0.5. Then what happens is two oscillators, right? Initial phase is something. After some time, they synchronize, come to 0 phase difference, and continue like this. So phase difference, if you plot, it looks like this. Now take the coupling strength to be negative, minus 0.5, again symmetric. Then no matter what the initial phase is, it will go to a final phase of pi. They will go exactly out of phase and synchronize like that. Now you see what is happening, right? Actually my coupling strength can be any real number, as long as it's symmetry. If it is positive, I'll have 0 phase difference. If it's negative, I'll have pi phase difference. That's very restrictive because my ultimate goal is to reconstruct the brane, right? Which means I should be able to get any phase difference and any frequency also. That's a different thing. Here, even the phases that I'm getting are only restrictive, very restrictive, 0 and pi. So how do you expand this limitation? How do you overcome this limitation? So any ideas? How do you overcome this? Because we ignored one important feature of the model. We assume that the connection coupling strengths are real numbers. Why? They don't have to be real numbers. Because the state itself is a complex number. Why should the coupling strength be a real number? So we'll make the coupling strength complex number like this. Okay, and since we are assuming symmetry, you need symmetry in the connection. So symmetry in complex domain means conjugation. All right, if you have n units, you have symmetric connections. Symmetric matrix means it's a Hermitian. You'll have to do conjugation. So this is a into e power I5. This is a into e power minus I5. If you do that, you can do simple algebra, right? Very simple derivation to show that the phase difference at equilibrium at steady state will be equal to the angle of this complex number. So with this feature now, I can use a complex coupling constant, and by playing with the angle of the coupling constant, I can produce arbitrary phase difference. Okay, this is already a big step forward, and initially we found this ourselves. We were very excited, oh, it's a new discovery and all. Then we dug up a book by Hoppenstadt and Izikevich. They have already presented that theorem. Okay, so it was a bit of a disappointment. But anyway, we found something else which is not there in the book. Okay, you can show a simple numerical example. Right, the phase angle is pi by 4, and you see the two oscillators synchronized at pi by 4. Fine. So one step, yeah. No, resonance we have shown. Single oscillator shows resonance, which means if the input frequency matches the oscillator frequency, it gives high amplitude response. That is there. Now we are looking at two coupled oscillators, and then we are just seeing what happens. If the connection strength is real, right, then if it's a positive real, then you get 0 phase difference, negative real. So I'm saying that's very restrictive. I want to get arbitrary phase difference. That's 37.4 degrees. How will I get? The answer is the secret lies in the coupling constant. Make it a complex number. Then the angle of the coupling constant will be equal to the phase difference that you get in steady state. That's what you can show theoretically, and you can also show numerically. I am trying to basically construct a network of oscillators which is general. Many frequencies, many phases, and trainable. So I can make it behave like the brain, I can make it behave like something else, right? So I'm telling you, this is a big challenge because we look at oscillator networks, what people use. They're very handcrafted, they work for only that few domains. They're kind of a general, super powerful models you find in AI. You don't find them in oscillator. Oscillator field is huge, it's a centuries old field. What we are able to do with all this theory is construct that kind of a very general, trainable oscillator networks. So I'm trying to build the theory to present those models towards the end. Okay, so what we are able to achieve so far is two oscillators, same frequency, but arbitrary phase difference. So far so good. But it's also not good enough because I should be able to get oscillators of any frequency and any phase difference and so on. So how do you get that? So we'll take one step forward because arbitrary phase frequencies is very hard. We'll take a pair of oscillators with only slight frequency difference. So omega 1, omega 2 are approximately equal, not exactly equal, but approximately equal. Then what happens is, if you use a strong enough coupling constant, you can force them to come to some kind of a common intermediate frequency, and after that they will go in sync. Okay, this is what is generally possible. So if you do a numerical simulation of that, I take two oscillators, omega 1 is 2, omega 2 is 2.2, very close. Epsilon is the coupling constant. So when epsilon is 0, you can see that both oscillate at the same frequency, their own intrinsic frequencies, 2 and 2.2. But as I increase epsilon, what happens is they are forced to come together. Like yesterday I went to some medical school here and to request somebody for collaboration. That guy is a doctor, I am an engineer, and then there's a frequency mismatch, right? He's saying, you cannot force me to collaborate, I don't like to collaborate, okay. So that's exactly what is happening here. So you have to increase the coupling. If you have some forcing signal, here it will be usually funding availability. That's what will force people to talk. I didn't have funding immediately, but otherwise I would have forced him to talk. So you have to increase the coupling constant. Then the two frequencies come together, and beyond some threshold value of coupling, they come to exactly the same value. And after that, they synchronize. Only thing is, they'll have a non-zero phase difference. The originally faster oscillator, which is number 2, will lead the originally slower oscillator after they come to a common frequency of 2.1, like the mid frequency. But that's also not very helpful, because by forcing them to come to a common frequency, I lost the frequency diversity. I want them to be what they are, and then also be able to talk. How is it possible? It almost sounds like a contradiction. Because the idea of a phase difference itself is a problem. Okay, I'll come to that in a second. Right. Phase difference is applicable only when the frequencies are the same. When frequencies are different, how can I make them talk in any meaningful fashion, in a reliable fashion? So I'll come to the big question in a minute. But I want to first highlight the kind of challenges that are present when you try to connect two oscillators and make them talk to each other. So that is captured by this beautiful plot called Arnold's tongues. So this is a well-known thing in dynamical systems. We didn't make this up. So here x-axis is showing the coupling constant, this epsilon thing. So I'm having two oscillators, frequency omega 1, frequency omega 2. I have some coupling constant epsilon. Now, how will they come to any meaningful phase difference? So this is a question, what this plot is showing. Let us start with 1. A frequency ratio is 1. Then let's say I take two oscillators with frequency ratio of 1.13 or something, not exactly 1. Then they won't have any phase difference, right? They can't talk. So I'll have to force them to come to a common frequency. So I do that by increasing the epsilon. If I'm here, I increase epsilon up to this point, enter this yellow zone, where they become synchronized. What does it mean? The frequencies come to 1:1 ratio. They come to a common frequency. After that, there is a constant phase difference. Phase difference is possible only when two oscillators have the same frequency. Otherwise, phase difference is not even defined. So I have to have sufficiently strong coupling to make them come to a common frequency. So this yellow curve, this looks like a tongue, right? So they're all called tongues, Arnold tongues. Arnold is a famous Russian mathematician, B.I. Arnold. Okay, so similarly, if you have let's say 2:1 ratio, I'm close to 2:1. Instead of 2, it is like 2.375 or something like that. That's the ratio of frequencies. Then they cannot talk, So then what you do is you increase the coupling strength up to a point when they'll only come to a simple integral ratio, 2:1. They'll come up to 2:1, and after that, that angle, this thing. So when you have if it is 1:1, you call it synchronization. If it is any other number, you call it entrainment. This is terminology. They can get entrained to a simple integral ratio of frequencies. So what I'm trying to say is, the theory of coupled oscillators is very, very painful and it's a very delicate field. Right? Our hope is to couple hundreds of oscillators and train networks, and it's a dur ki baat, what they have called dur ki baat. So how do you get over this problem? So now first thing is the idea of phase difference. Right? When you moment you talk about phase difference, your frequencies are assumed to be the same. So that's not a good quantity to look at. I want the frequencies to be whatever they are, and still I want a reliable phase relationship between two oscillators. How can you talk about it? Consider this. Take the phase of the first oscillator, divide it by its own frequency, omega 1. Phase of the second oscillator, divide it by its own frequency, omega 2. Take the difference. This is some kind of a normalized phase difference. Now, when two oscillators are talking to each other, can we have a constant normalized phase difference? Can I make that equal to any desired? I pick a value, I want to make this equal to that. Is that possible? This is possible. But it's possible only when you have special equations. I'll show you what they are. The idea is, intuitively, the idea here is, if I have some oscillator here of frequency omega 2, it's getting inputs from some omega 1 and omega 3. Okay, omega 1 is a high frequency signal, omega 2 is intermediate frequency signal, omega 3 is a low frequency signal. So 2 fellow is getting inputs from those two, both of these 2 fellows. What should happen is, at the connection, when this is going over the connection to here, this frequency must be instantaneously transformed into the frequency of the listener. Right? Same thing should happen here also. Then what happens is, every oscillator will be listening to the inputs in its own frequencies. So there's no problem of entrainment or synchronization. Everybody is happy. It's like, these days you have apps, right? You go to Japan, let's say you don't know Japanese. You ask in Telugu, whatever, e cake enta, right? And then it will instantly translate, and then the other guy hears in Japanese. So if that is there, then everybody is happy. Nobody has to come midway and meet the other person, and there's no need to force collaboration and all that stuff. How can you instantaneously transform frequencies? This is where the beauty of complex formulation comes. So each frequency is this, right? The oscillation is like given like this. Z1 is equal to A1 e power I omega 1t. This is oscillating at omega 1. How do I translate this instantaneously to omega 2? Very simple. Raise it to the power omega 2 by omega 1. It becomes omega 2. Right? So take this complex number Z1, raise it to the power omega 2 by omega 1. Its frequency instantaneously switches to another frequency. Use that term for coupling, right? Not Z1 itself. How do you do that? So if I have 2 oscillators, this signal goes to the other side. Here at the connection, you raise Z1 to the power omega 2 by omega 1. There's also some coupling constant. That goes as input to the second flow. So in the reverse side, in this connection, this state Z2 is raised to the power omega 1 by omega 2. That's what you send to the other side. Equations will look like this. And you have to do a little bit of algebra to figure out exactly what should be the form of the coupling string. If you decide that, if you work it out properly, you can show that by normalized phase difference, I can make it equal to arbitrary constant. So now give me any 2 oscillators, arbitrary frequency omega 1, omega 2. You give me some phase angle. I can couple them using these equations in such a way that the final normalized phase difference is equal to your chosen angle. And it's an equilibrium state. You disturb it, it will come back to that same angle. And this theory was not present in literature. I mean, there's like this literature of oscillator networks goes back to, coupled oscillators is at least centuries old. We call this special kind of coupling power coupling, because you raise to the power, right? And you can show numerical examples that it works. Okay, so now we propose that this is a kind of, if you want to model clusters of neurons as an oscillator, and then they're coupled, we propose that this is what is actually happening in the brain. So reviewers went wild. No, this is just a mathematical nonsense, this is not what is happening in the brain. Then we try to argue, Bhaiya, no, it's not. You think closely what is happening actually in the brain. You can interpret what is actually happening in the brain in terms of our power coupling. Then I think somehow the reviewers bought it and paper got published. This was the first paper in this line of work. Okay, so now we are set up, right? What have we achieved so far? Now I can take any pair of oscillators and couple them so that you can get a constant desired normalized phase difference. You can easily extend this to n oscillators, but for any pair in the n oscillators, I can get some desired, so you can have an n by n matrix of connections and power coupling and all that stuff. This is straightforward. Now, question: how do you train this? How do you start doing meaningful things with this? So let's go forward. When it comes to training, the first thing that you can ask is, how do you train a single oscillator? Okay, I'll wrap up. How to train a single oscillator? So you have, I can train its frequency. It's called frequency tuning. So you can see that if I give you some complex input, complex exponential, complex oscillation, you can tune its frequency. Let's say oscillator is going at very high frequency, input is going at low frequency, right? oscillator frequency will tune itself to the input frequency, so you can train that. Now how do you train a network? I take a layer of coupled oscillators and then take weighted sum. Okay, this can be trained to produce any time series, not just any brain signal. So we've done it for two simple time series. It learns well. First you train the frequencies. You see that frequencies initially are all pretty much random. Then you give only a signal which has only 3 frequencies, and all frequencies get clustered around those 3 input frequencies. And then we have given more complicated EEG signals to train. It learns very well, both in spectral terms and in time series, time domain. It learns the signals very well. This is starting point of building large scale models to actually model high dimensional brain signals. So we did some initial work first with the EEG data that was published last year. We took data, EEG data from sleep, right, waking and sleep stages from Sujit Vijayan. In this case, we had a hidden layer to these oscillators, and it learns it very well. The loss drops by an order of magnitude when you add this hidden layer. I can send you the papers. We have done something similar with fMRI. For reasons of time, I'll just skim over this. But basic idea is the same. With the hidden layer added, so hidden layer means input layer is oscillators, hidden layer is sigmoids. And then you can train this using some kind of a complex backprop learning rule. It learns very well, and this was published again some time ago. Then a model of self-organizing map, right, where you have map of frequencies. This kind of maps are seen in the cochlea, in the inner ear, and also in the auditory cortex of animals. A lot of work is done on bats, because bats fly around with sounds, right? So they have a very rich auditory system. We were able to model that using a 2D array of oscillators, just like a self-organizing map. And we modified equations to capture all this. Then we also modeled locomotor rhythms. Okay, that's a very good problem in biology to model with using oscillators. This is a circuit model. We use what's called a VO2 memristor. This produces oscillations which look like this. It so happens that that also is similar to one of those biological oscillators called Morris-Lacquard model. So we just took 4 oscillators of that VO2 memristor, coupled them with 4 capacitors. By playing with the capacitor values, you can produce all these different kinds of locomotor rhythms. Quadrupeds have rich variety of locomotor rhythms. Humans just walk fast, walk slow, nothing much happens. But quadrupeds have rich variety like gallop, canter, trot, and all pace, all these things. We can capture all of them using this. Then this is the deep oscillator network I was talking about. Right? It will have alternate layers of oscillators and some sigmoid or ReLU or whatever. I can train the whole thing using one of these optimizers, like what you do in deep networks. It learns beautifully. I'll show you some simple examples. This is just an autoencoder. It learns well. Integration, that involves memory, right? So it learns that well. Some signal processing task, demodulation, it learns that. And some more complicated deep learning kind of tasks, standard data sets, action recognition from video. It beats the competing models. All this is published. I can send you the papers. Next video frame prediction. It beats its corresponding comparable LSTM model, and also more compact. So one thing I feel is these oscillator networks can be like a good connecting point between 4 major fields: deep neural networks in AI on one side, complex systems, the whole field of complex systems. The neuromorphic engineering is hardware, neural hardware, and computational neuroscience. It can bridge all these 4, and that can be grand synthesis. And in my lab, the big goal in neuroscience is come up with an oscillator theory of brain. Describe all brain function in terms of oscillators. Because the problem is, suppose if you look at motor field, motor science, right? If you are doing a punching action or reaching action, they have one kind of equations. If I am doing walking or if I'm doing something like this, they have oscillator equations. That's not fair. Because whether you're doing punching or whether you're doing this, the brain is the same. So you need to have the same model, and which is always oscillating. So you need to show how all activity can be done by oscillating networks. That's a proper model. So that's our goal, not only motor function, everything. Autonomic control, how do you control gut and heart and all these things. Oscillations of mood, bipolar disorder. We have published a paper on that. Right? Memory. In memory, for example, working memory is encoded in terms of theta gamma oscillations, right? The big picture, I'm just wrapping up, is that think of brain as some kind of a radio communications medium. So radio communication, the range of communication frequencies is just 3 Hertz to 3000 gigahertz. If it goes less than 3 hertz, the wavelength is so big that it goes much bigger than Earth's diameter. The signal doesn't come back. If it goes much bigger than 3000 gigahertz, the transmission cost becomes so expensive that it becomes impractical. That's the range. So like that, brain seems to be operating from 0.1 hertz to about a couple of hundred hertz, because that's a frequency that the brain's tissue can support. So then, just as you have your frequency allocation, 5G, 4G and all that, right, it's very expensive, so you auction it and sell it. Brain seems to be allocating different frequencies for different functions. This is for vision, this is for touch, this is for motor, whatever. And what is the basis of that allocation? We should look at purely as a computation problem. Right now, it's mountains of empirical data in oscillator and neuroscience, without any logic, without any deep theory. Whereas what I feel is, if you take this kind of, we have the code, you are free to take it and run it on all sorts of data sets. What is the logic of the frequency allocation? If you understand that, you can come up with a grand brain theory of oscillation, of neural oscillations. Okay, so yeah, these are some students and collaborators who worked on different aspects of it. Thank you. I just want to announce one small thing. So we keep conducting workshops. Next month we have a workshop on AI applications in EEG processing. If you go to our website, you can see that. I might have a startup called Neurogati. So you can go to the website and get the information. Thank you. The topic is still young, obviously. We just got the basic network working, some basic results, but now the real game starts now. We have to try it out on all sorts of problems and. Yeah.
When you were wanting the neuron by RC circuit,
yeah.
That is called as the lump parameter model.
No, that's the leaky integrated fire neuron model. We are not using it.
Okay.
That's a spiking neuron model. I just gave you as a background information. Our models are all oscillators.
So it is not based on that RC circuit?
Our model, no. But having said that, we are building a hardware model of our oscillator networks. Now we are collaborating with somebody in EE department, Dr. Aniruddhan Sankaran. In fact, we have plans to start a startup, second startup based on this. The idea is to build hardware models of these oscillators, because the whole motivation is to build these low power realizations. And we do see that in our simulations. We haven't made a chip yet. The simulations show that it is really low power. And as a network, it's very powerful, just like your CNNs and RNNs and all that.
So actually, I'm using the similar strategy to understand the fluid dynamics. So there we can integrate the transmission line models. So can we integrate here as well? Like instead of concatenating all the RC circuits, can we make a transmission?
No, but this is not like compartment model. I want to understand your problem better. So here, you can use it in two modes, deep network mode or also in an associative network mode, all-to-all connections. You can store memories in it. Have you heard of Hopfield network? Yeah. You can use it as Hopfield network for oscillations, for oscillatory states. But I don't know if your problem fits in one of these two.
Yeah, it depends upon the physics.
I want to understand, sit with you, understand how it works. Yeah, the maps, brain maps. Yeah. No, visualizing the.
So one of the work you have solar.
This one. This one. Oh, here basically you have a series of video frames. The problem is to predict the next frame based on the past frames. You have the memory of past frames. That so our model is this, and this is the LSTM model. So you see the quality.
So the last slide you showed that separate brain functions like motor or attention. So but they are not working in isolation. So how oscillations in attention versus oscillation in motor function? How will they?
Yeah, I mean that's the idea. You have to do it that way. Ultimately, you have to. The model will be a sensory motor function, not just pure attention. Yes.
Same logic of that.
Yeah, the network elements will be now oscillators. See, it is just that we are not used to thinking on those lines. For example, when you study motor function, when you study models of motor function, where do you see oscillators? Almost never. but they are there all the time. Some experimental data will only talk about gamma involvement and theta involvement, but what is the theory for that? So this network, once you simulate like this, you'll have the theoretical basis.
Practically similar to the quantum mechanics.
Yeah, yes, yeah.
Finite polynomial.
Exactly, yeah.
But the corresponding operator algebra could have been very, very significant.
Yeah.
For example, if you can establish the computational relationships and apply elegantly the Lie algebraic formulations. I'm just
No,
thinking
please.
about
We want real help from quantum mechanics. I'm trying to enthuse one of my colleagues. He keeps saying later, but if you're interested, we can have a talk. Because whole matrix mechanics, you can think of it as an oscillator network. Frequencies are getting transformed by matrix transformations, right? This is exactly what it is. In fact, we're developing a model of spatial navigation for hippocampus. So the input, so what happens, brain gets inputs through limb oscillations when you walk. And that's integrated to find out where I am. So you have to take 4 steps forward, and now I know that I'm from point A to point B. This is what is called path integration in biology. Now, I can train network to do that. So what will happen, it looks like the hidden layer will now start looking like a wave function, psi of x comma t. Right, x is the position. And output is, you are predicting position or momentum, a velocity. So it is like a position operator applied to wave function giving you position, or momentum operator applied to the wave function giving you momentum. So the network is behaving like you extract the wave function from the input data, and on the wave function you apply these operators to get position and momentum. So there's a very beautiful analogy with quantum mech, but I want somebody in the field to kind of give it the rigor that it deserves.
Neeraj's question that
Oh.
every action, if you can quantify and collaborate with an operator,
Correct.
and we have the same wave.
Yeah.
And that can be an
See, operator here will be like a network stage. That's an operator in our terms.
This mathematics is so simple.
Very similar.
Very simple.
Very simple,
Very
yeah.
well established.
Yeah.
So in alignment with that question, like this physics informed neural network and this behavioral operator, etc. Right? Because most of them you're having the models from PTEs. So you're having signals and then outputs. on.
These are ODEs, but it would be nice to do PDEs. We haven't done it.
Okay.
If you have that kind of background, we'll love to collaborate. Because what happens is there are very deep mathematical problems even here. See, consider the problem of raising a complex number to a real power. Complex number to integer power is fine. The moment you have a rational power, it becomes a whole hell breaks loose. I mean, you have a Riemann surface and all. I don't know what the hell is going on. We're talking about any real power, right? Numerically, it's fine. MATLAB doesn't complain, Python doesn't complain. But I don't know what kind of theoretical issues arise. So that's where I need help from hardcore mathematicians. Yeah.
One quick question. Wonderful talk. I really enjoyed the spiking neural networks idea. But let's say if I want to implement it on hardware level or I want to take it on the application level. So there are only few processors available on spiking neural network, but fundamentally they are.
No, but this is not spike neuron network. We are talking about a whole class of networks called oscillator neural networks.
Okay.
And you have oscillator circuit models.
Okay.
So that's what we have developed. We have developed the whole network is converted into a circuit model. That's what our startup basis is.
Got it. Thank you.
Okay, we can always catch up, but thanks a lot.
So I would like to invite the organizing committee member, Dr. Neeraj Kumar, to join us in the
Thank you. Where's my bag? My bag. Oh, sure.
Thanks very much for joining hands with us in this very, very important pair program. And this is a very, very interesting program where now government thinks that people should join together and grow together. And that's something very happy to have Srinivas garu also joining us, that it's time that individual institutions trying to grow. I always tell to people, when you grow, everybody around you also should grow. That is a true growth, otherwise it's not a growth at all. Otherwise I will even go to the extent to call such growth as a cancer. Okay? So, because cancer is also a growth. So let's grow together is something that we always believed in, and IIT Hyderabad has been doing a lot of things in that direction, and now that we have got a chance to work with all of you to see how together we grow and ensure that the country grows. That is something I think we should always keep that in mind. What are we contributing to the country together is very important. Individually, each of us can do small things, but together a lot of synergy can come, that 1 plus 1 can be significantly greater than 2 is what we believe in. So let's see how do we work together. We have set up reasonably good facilities at IIT Hyderabad. I would like to see all of you to use it. For example, very recently we have set up a microscopy center here. We call it as In situ and Correlative Microscopy Center. First of its kind in the country, 80 crores we have spent it. And then in that, NIT Raipur is sitting here by any chance? Okay, so you have given, you are a partner in that. We have about 20 partners. Each of them gave approximately about 1 crore or so. And then the remaining 60 crores came from the DST, and we have set up such a center. And a lot of research in the healthcare can be done. So, for example, we can do in situ microscopy of a cancerous tumor. For example, by heating, all of us know hyperthermia, we talk about. If you heat a cancerous tumor to 50 degrees, it's supposed to die. But what exactly happens to a cell when you heat it to 50 degrees? What is happening at an atomic level and at the atomic level? Can we see it in a high resolution transmission microscope? Something like an aberration corrected TEM. We have 2 aberration corrected TEMs in this particular center, which we would like to use and see how such things happen. So put a cancerous tumor cell in a microscopy. Oh, you need to record it by any chance? Yes. This voice is not sufficient for you to record?
For broadcasting we need.
Oh, you are broadcasting. So there are some people joining online?
Yes.
I'm sorry.
They requested us for bigger reach too.
Sure, very good. Sorry friends for starting before this. So this is something we would like to see, and many of these things to set up in every place is also not easy. For example, we have set up these 2 aberration corrected TEMs. That itself was about 20 crores, 25 crores. And then we have an atom probe set up. Again, if some of you want to see anything, a biological species, for example, only thing is you can't see live species in an atom probe, because we cool the sample to almost 20 Kelvin, because we want to freeze the atoms so that the location of atoms can be seen. This is one microscope which is like a CT scan. We all know about CT scans of a body, but here you are doing a CT scan of a material at the atomic level. Okay, CT scans that we always know are at some micron levels that we do, and stitch the layers and get a 3D information of a particular organ of your body and things like that. Here we are doing the same thing, but at the atomic layer, layer by layer, atomic layers, you can get information, stitch all these layers, and in 3D you can see where which atom is sitting, where which molecule is sitting, for example. This is something which is amazing, but because you need to freeze the atomic locations, XY coordinates of the atoms in a particular layer has to be frozen so that I can see the atom exact locations. And for that, for example, if I have a steel, I am a metallurgist, I want to see where is iron sitting, where is carbon sitting in a steel. And if I have a semiconductor, I dope an element into the semiconductor, I want to see where is this dopant going and sitting. So for that you need to have the XYZ coordinates of atoms to be frozen, and that is the reason why in atom probe we freeze the sample to 20 Kelvin. So that's the only stumbling block for those people who want to always look at live species. But there is a lot of research that can also be done with frozen biological species and get a lot of information. So please feel free to use all this. And under this ANRF pair program also possibly some more facilities are going to be set up. So our goal is to see that certain facilities come to your individual locations, so that you are not handicapped, that there is something available, but something which is of a much higher cost can be set up at a centralized location where you people can come. In fact, for your information, we have also set up on November 15th a microscopy training center. This is India's first microscopy training center for the whole country. A company called Geo, which is a Japanese company which makes microscopes, have given some freely one SCM to us and refurbished one of the existing TEMs. And with that, we have now set up this microscopy training school. About 3-4 years back, we started a new initiative of teaching people all over the country by something called OAT. I do not know how many of you have heard of it. If you are interested, go to Google and search for OAT at IIT, which will tell you this is called Open to All Teaching. I always believed that when somebody wants to learn, there should be no barriers. Nobody should ask you what is your background, what entrance exam you have written. In India, we have too many entrance exams for everything. So we say that let's remove all these barriers, let people learn the way they want to learn. Okay? I'm a metallurgist, I suddenly want to learn some AI. Okay? I don't want to join an AI degree, but I just want to learn one course on AI, basics of AI. I should be able to attend wherever an expert on AI is sitting, and I should be able to learn that. With that intention, we converted many of our classrooms into hybrid classrooms, and we started asking our faculty, are you interested to teach whatever you are teaching in a regular class to an outsider also? Okay? The moment faculty says, I am okay with it, we open it and we put it on our website, OAT at IIT, where we say, here is a course, this is the course content, this professor is going to teach this course, and here is the timetable. So the timetable is fixed. So once the timetable suits you, you can be from anywhere in the world, and you can sit in the class online. The moment you register for the course, we give you a login password for that, so you join the course from anywhere in the world. In fact, I teach a course every Tuesday and Thursday evening 6 to 7:30, and in my class I have students from Sweden, I have students from Malaysia, Singapore, Doha, a variety of students, about 15 students from all over the world sit in the class live on the screen, and there are a few students physically in front of me, and we are able to teach in a hybrid mode that way. So this is different from NPTEL. NPTEL is more like a passive way of learning for me, because I only hear what the teacher is teaching, but I have no way to ask a question to him. Okay? I am not live in the class, whereas here the student is live in the class, and we tell them that anybody can join. It can be a student, it can be a professor like you, it can be a working professional, it can be a homemaker, it can be 80-90-year-old man or woman. We say let anybody learn. Okay? There should be no barriers to learning. And I tell my colleagues, don't control the entry, control the exit. Okay? So that's what matters actually. So let anybody join. As long as you pass my exam at the end of the semester, I will give you a grade and I will give you a certificate saying that you have done this course from IIT Hyderabad with these many credits and this is the grade you got. What you want to do with that certificate is up to you. Okay? So we started this. Last 3 years it's running. A number of courses are lining like that, if you can look at. And we are now planning to start this microscopy training also with that manner. So we will have a number of courses on microscopy offered to people all over the country. Why all over the country? Anybody in the world, in an online fashion, the theory course to begin with. And if you get a B grade in the theory course, you are welcome to come to IIT Hyderabad. Stay for a month to 3 months depending on which microscope you want to get trained on, and we will be able to train you on the microscopes. So that, and not only train you, at the end we conduct a drive test, and if you pass the drive test, you become an official user of our microscope. Okay? And once you become an official user, we have, if you go to Sathi Syscom website, there is a place there where you can block a slot, provided you become an official user. This is open only to the official users and also to the partners. Okay? There is a coordinator in every partner institution that people can log into that and then book a slot. So I want to come on so and so day with my sample. Just come, and you will not have any operator operating it, you will operate it yourself. and knowing pretty well that people, if they don't regularly use it on a daily basis, they will also forget. We are also going to offer this training on a semester basis, so that once again you can keep on coming again and again and get trained. So this way our whole goal is that all of us work together and learn together and grow together. So that's the whole concept. We want to see how the whole country gets use such kind of opportunities that are available, and I think ANRF PAIR has given us a good opportunity to come together, work together, and I think we should utilize this in the best possible way. We also see that we would like to see people like you, there are other programs also. For example, INSA, Academy of Sciences have this program, mentoring young faculty. I hope it is still running. You can happily come. I used to regularly get a lot of such faculty members from other institutions when I was in IIT Madras. They come for summer, stay for 1 month to 3 months, and this also helps you because you come and initiate some research and then get some preliminary results, maybe write a paper on that, then submit a DST proposal or a NRF proposal or some such proposal. When there are some initial results available, then your proposals getting sanctioned becomes much more easy. So these are all opportunities for you to start working together, get some preliminary results and say that I am already working, because when a proposal is sent to any agency and reviewers are looking at it, they want to see whether the person has some experience in that field or not. Suddenly you jumping in, those days when nanotechnology started, everybody wanted to do nano. So whether they have any experience in nano or not. So but then sometimes proposal gets sanctioned, some proposal does not get sanctioned. But this is one way. So utilize this PAIR program to keep coming. We are welcome. We have a 320 capacity guest house, possibly the largest guest house among IITs. Happily come stay here. And then possibly very soon we are also planning to build a block which is called Visiting Scientist Block, where we can have a kitchen for you, where you want to cook stay for a month or 2 months and cook. So that's also another which will come very soon. Right now we have one what is called MSH, married students hostel or a housing, and that is meant for typically for PhD students. But whenever sometimes we have free, we also give it to people like you. So come, stay here, and then preferably after some time when you become too busy, you can keep on sending your students. Once a connection is established, it's going to be wonderful. I know it will, many of you I can see very young people, so all of you will have at least 25 more years of professional life minimum, and it's good to collaborate at the early stages and learn from each other. Okay, so that's I think a few points that I want to ask. If there are any questions from you, what a director of the PAIR hub can answer, I'm happy to answer. If there are any difficulties that you are facing or you want something else to be done, I mean, IIT Hyderabad system is very flexible. We want to make a lot of things happen and see that everybody learns together. We also have started a number of online masters programs. Nowadays NEP allows anybody to do even 2 degrees simultaneously. Okay, I have seen a lot of people doing it, and age is not a bar. Okay, so happily you can register for such MTech programs if you are interested, and possibly even get an MTech online MTech sitting. For example, we have even started, if some of you not connected to this science program, we have started a Department of Heritage Science and Technology at IIT Hyderabad. Possibly the only engineering institution in the country which has that, and we started an MTech in Heritage Science and Technology online. Okay, and usually for an MTech you need a BTech to be there, but here is an MTech where any degree is welcome. You can be a BA, you can be a BCom, you can be a BSc, okay, just passing one particular degree and attending of course our interview, and if you are selected, no gate need to be written because this is not an engineering program. So you can happily register, and quite a number of people are registering and getting their MTech degree on Heritage Science and Technology. So that is the level to which we are going, and we want to make things as open to people, as flexible to people as possible, to see that everybody gets benefited. by the initiatives that we are taking. One more interesting point also is we have a very strong support for entrepreneurship at IIT Hyderabad, for your information. Particularly you are talking of healthcare. We are very keen. How do we, for example, all of us know that in any hospital, most of the instruments are all imported. We don't make these, whether it is X-ray or ultrasound or MRI, anything. We have a faculty in biomedical who is now trying to make an MRI. We have already another faculty who already made not just a diagnostic tool. I mean, ultrasonic is used as a diagnostics tool. We all know that, but as a therapeutic tool, he is now has made that, which particularly meant for the breast cancer cure. He is trying to cure the tumor, I mean, using the ultrasonics, because we all know that with radiotherapy there are a lot of side effects. That this is one which we expect that it will have very little side effects because there is no heating involved in the process. Okay, so that is something which we have developed, and we even have a master's program which we call it as Medical Device Innovation MTech, where a student spends 6 months in a hospital and then talks to the patients and doctors, picks up the problem. At the end of the 2 years, the student has to develop a product which is a prototype of a medical device, and his whole thesis is a product. This is possibly India's first product-driven master's program. No thesis need to be written. All of us, when we write do an MTech, we write a 100-page thesis, which we ourselves will not read it the next day after submitting the thesis. Okay, so can we recreate that? We also created a department of entrepreneurship now, and it offers another MTech program which is slightly an upgrade of this program, where we call it as an MTech in techno entrepreneurship. Okay, where at the end of the 2 years the student will not only develop a product, it can be any product, okay, but also to have a business model along with the product. So one engineering faculty, one entrepreneurship faculty or a science faculty will come together, where the science and engineering faculty will teach the student how to make a product, and the entrepreneurship faculty will teach the student how to sell a product. Okay, so this is also very important. So we feel that institutions like us should ensure that more and more of things like this happen. And in fact, we strongly believe that such kind of products to be made, you need to have a lot of intuitive ideas, and out of box thinking can come only when you have a lot of intuition. And we believe that creative arts can induce intuitive ideas. We have set up a center for creative arts. Yesterday there was a big program. I don't know if you were there yesterday. Yella Venkateshwara Garu is a Mridangam artist. He is known to be Nava Mridanga Vidwan. He was here. He has become a visiting professor with us. We have about 10 Padma Bhushan awardees artists who have become distinguished professors at IIT Hyderabad under this center called Center for Creative Arts. We want to bring all of them and ensure that the students also start exploring things beyond engineering. Engineering is all too much of a left brain activity. So how do we bring the right brain activity so that we are more balanced in life? So things like this, for example, at IIT Hyderabad, no BTech student can graduate unless they do 10% of their total credits coming from liberal arts and creative arts. So we have made it a mandatory for every undergraduate student that they do a number of these courses: music, dance, painting, variety of them. So this is something that we have started, and we would like to see how we can support innovation. And a lot of interesting programs. We even have a BTech program where almost there is no curriculum. Okay, first time again in the country. We thought, let us give freedom to students so that they create new things. Okay, so this is called BTech in Engineering Sciences, where 8 semesters the student can choose what he or she wants to study. Okay, so I always tell to my colleagues that at 18 years of age you can decide who can be the Prime Minister of the country. Then why can't you decide what you want to be? Why should you get carried away by what your uncle says or parents say or somebody else says? So we are grown-ups and we should be able to decide. So we have started like that. We have started even encouraging students to work on their innovative ideas. Every semester we call for proposals from our students. We call them as build projects, bold and unique ideas leading to development. If a student has a good idea, we start giving them 1 lakh rupee to begin with, and then more money we can provide as they grow. And we also tell them, if you want, take a semester break. Don't do any courses in 1 full semester. Work on your innovative idea. At the end of the semester, we give you 6 credits. Show us a product, take 6 credits. Okay, and this is something that we have been able to achieve, and we also got approval in our Senate to say that at the end of second year, if the student, BTech student, does not have any backlogs, they can take a diploma from us and stop studying and start their startup, sitting in our hostels. Okay, and we say that we give you 5 years time. In case you fail in your startup, come back and complete the third year and fourth year and take the degree. But ideally speaking, we want all of them to succeed and come back and tell me after 3-4 years saying that, sir, I don't need your degree. Okay, I'm already successful. Okay, I don't want to now waste my time sitting in the class for 2 more years and get some degree which may not be useful for me at all. Okay, so this is what is important, friends. In India, we need to create such kind of an environment where things are built. Okay, in fact, this year we started one more interesting initiative. We call it as Bharati, bold-hearted aspirants raising to transform India is the name we gave. Okay, where we have 600 undergraduate students who have joined. I connected them with about 100 faculty members, very young faculty like Sandeep and Aravind and all of them. Okay, and we tell them that your job is just every week have a cup of tea with these 6 students that I am providing to each of you. And these 6 students are interdisciplinary, they come from different branches, so they are not from the same branch. And I tell them that any amount of money that you want, I will provide you. Your job is to ask these students, what do you want to build with your own hands? Okay, we want to see India is built by our students. So they should be able to build things, and I want to see every hostel getting converted into a workshop where every day they sit and make things. And this is something that is happening now. First semester BTech student, I said if you can transform the first semester BTechs, everything will happen, because unfortunately, if you know, 20 years back, everybody used to join IIT to think that I want to become a great engineer. Okay, it's no more. People join thinking that they get a highly paid job, and where is that job, everybody knows. Okay, so as a result, people join, learn some coding, some soft skills, that's it. Irrespective of whether you are a metallurgist like me or a biotechnologist, it doesn't matter. So we thought India, if it has to become Viksit Bharat, you need really true engineers who will build things. So we started all this. And in fact, right now we have a discussion on our Senate happening, and everything goes well. This August we want to admit a few students whom we ask, after you clear your JEE Advanced, okay, tell us what have you built in your school. Okay, we are not going to admit you based on your JEE Advanced ranking alone, but we are going to ask you, have you built something from your 8th grade to 12th grade? Have you participated in national level some competitions on what you have built, and have you won some prizes? If so, we will give you a supernumerary seat, about 30-40 seats we want to create like that, who will come to IIT Hyderabad and from the first semester and start building things. Okay, so I think I would like to urge all of you, if you have students who have such kind of innovative ideas, feel free to send them to IIT Hyderabad. We have a building adjacent to this which is called TIP, you must have seen it, Technology Innovation Park, 1.5 lakh square foot building. We have actually 2 buildings, one is called TRP, Technology Research Park, where any industry can take a space and collaborate with us. Whereas the second building, we call it as TIP, which is only meant for startups and pre-incubation ideas. We give freely space to students and student of any place or faculty of any place. Okay, so if you have some innovative ideas, just be in touch with us. We have a Dean of Innovation, Translation and Startups. Okay, we will connect you with the Dean. Funding can be arranged. Just today we are talking to NMDC to get about 10 crores funding from them. So now companies are coming forward. They say we don't have time to do this kind of innovations, supporting innovations. You do that job, we'll give you the funding. Okay, so our job is to find out who are the bright people all over the country. In fact, I remember when our building was getting ready, I wrote to 3,500 engineering colleges asking that if you have any student who has a brilliant idea, please come. Okay, and we will give you funding, we will give you space, we will give you mentorship. Okay, and this is how we want to grow. Very recently on January 3rd, we organized Inter-IIT Innovation Meet. We have been doing Inter-IIT sports for a long time, and we thought we are not doing much on, so we called it as Inter-IIT UG Innovation Meet. Okay, undergraduate students of 23 IITs, we invited them. We said showcase if you have something to showcase. Okay, about 100 entries came, we brought all of them and we had a competition between them and we gave prizes up to around 15 lakhs worth of prizes were given to all of them. So, and also try to see if some of them can be connected with some industries so that some of their ideas can be taken forward to commercial reality. So all these we want to become a hub. The way we are a hub in this pair program, we want to be a hub for the whole country in innovation. And please feel free to come forward if any of you come across ideas, either you yourself have some ideas to build things. We want to be a hub and cradle for creating such kind of support which is needed for India to grow. So I think I will stop here. Sorry. Any questions? Feel.
Outsiders equipment company here.
Yes, sir. No problem.
Along with IIT Hyderabad.
Correct. In fact, I'll tell you, of all these things have led to approximately in the last 6 years or so, we have about 330 startups at IIT Hyderabad. And I don't think all the 330 are students of IIT Hyderabad or faculty of IIT Hyderabad. There are people from outside whom some collaborations have come through us, and they have raised about 1500 crores of revenue. 1500 crores. So this is the track record of IIT Hyderabad, and we have been able to do this because we believe that if you can provide support, there are brilliant ideas everywhere. Okay, just that support is what is needed. So we are ready to do. And I always tell my dean students to keep at least 200, 300 rooms free in the hostels anytime for people to come and stay in the hostels and work on their innovative ideas. So we are ready anytime. Okay. Thank you. Anything more? Why not?
15 are from chemistry and another 14 are from biology, pharmacy, and 2-3 are from computer science. The idea is you take PhD students if you know nothing about a particular area. You want to do something in electrical engineering, you know, you take a person from electrical engineering and something like that. So, now you all have come here thinking that IIT Hyderabad is great. Thank you very much for your thing, and then we got this pair program, and we will try to work together. But the thing is, in India we have a class system, right? IIT people should not talk to NIT people, traditionally. Why do we waste time? And NIT people should not talk to second tier, third tier institutes. But it's absolutely important on the part of DST to see that we all have to work together. And at, you have seen the energy of our director, very ambitious, very nice. And we have a program that from NIT, if somebody is more than 9 CGPA or 8 CGPA, they can come here and do their final semester without paying any tuition fee to IIT. And we found out that these guys are really good. Their retention to PhD program is several times more than the retention of our own BTechs in IIT. So, when we are talking about things in 2026, they are very different from 1996. Research can be done anywhere and everywhere. Today, I am going to talk about a very pedagogic thing about drug discovery, because in life sciences and biotechnology, chemistry, pharmacy, drug discovery is sort of a very interesting field, and the way in which this is going on is to be noticed, and the technologies are changing, and the problem is the same, right? And people, why do people make drugs? Any ideas? I don't know. Huh? To treat the disease, very good. And any other thoughts? Make money, of course. They are interested in only in making money. Even if there is no disease also, they want to make money. Okay, they want to sell their drugs. Okay, very good. So, that is one thought process. And for fun, because they want to publish papers. Aha. They wanted to get something, and they just wanted to, if I say that I published 340 papers and half of them in drug discovery, what does it mean? I do lots of useless research. Because if you do useful research, why do you publish? You develop a drug, right? Because if somebody is publishing in drug discovery, that means that they are doing useless research. It's not, I'm not joking, this is true. So, the question here is, we are entering into a stage where a country of 1.4 billion suddenly have more and more number of institutes. India is probably the best in the world in converting wealth to knowledge. Paisa de do, paper chapo. Very good. The best, bang for the buck, we are number 1, and number 2 is somewhere, number 3 like that. The number of papers that are published for funding. But in contrast, you wanted to convert your knowledge into wealth. We are very, very low. Innovation index, we are about 80. But somehow some politics and other things that they have done, they brought it to 40, but 40 only. So, now the question is, you are a knowledgeable guy, how do you make, hey, this is recorded, right? This can be used against me. It's okay, record it. No, it doesn't matter. Okay. So, now I have a typical situation. IIT, the best BTech students, the top 20% of them, their pay package is anywhere between 30 lakhs to about 50 lakhs or even 1 crore. An average, you take the top 20%. And you go to the MTechs. The top 20% of the MTechs, their pay package is around 15 to 20 lakhs, much less or half the BTechs. Then you come to PhDs. The top 20% of their pay package is between 8 lakhs to 12 lakhs. That's what the industry standards are. There is something wrong in it. If I am telling that go and then do PhD, is it a good advice? Will anybody with some sense will believe me? And why do you produce PhDs? That's another thing. Any guess? PhD is a pain for the students. You agree, right? Oh, Sandeepan is not there, don't worry. Okay. And PhD is a pain for the teachers. Okay. And they are bigger pain for the nation. Unless you are passionate about it. Why do you do yesterday that Yella Venkateswara Rao, one of the great Mridangist, okay, Nava Mridanga Vidwan, and then I saw Yella Venkateswara Rao's Mridangam when I was a teenager. Why does he do it? Why does somebody sing? Why does somebody dance? Why does somebody do different things? Now, we have to first of all understand that we are not really associated with a particular branch or a particular thought process unless we believe in it. How do you define that? What is the motto of somebody that they want to do PhD? You should be nice with supervisor just in front of him, manage some papers, get all these things and get your PhD degree, and then ask somebody to give you a job. The worth of a person with a degree and without degree, will it be huge or not? Is a more value attached to degree or to the worth of a person? Somebody in an NIT or in a college and IIT, what difference will it make based on the position? If you were to name one important contribution that India has made the last decade in research, is Chandrayaan. No doubt about it. There is zero contribution from IITs, zero contribution from NITs. It's a local college in Thrissur with very limited funding and very, very limited support from the government. Despite all odds, they have achieved it. And when someone asks what exactly that a great institute has done, we need to think about it. Why we need to think about it? Because we are transforming from an export-oriented education model to a talent-retaining education model. Because if you have a son or a daughter, what do you want to do? You want them to get very well educated and go abroad. Because when I did, because now I am 60 plus, when I did my masters or BTech, there is nothing that you can do in India. But the quality of Indian science is very high. Anyone has an idea, now who is the world leader in science and technology? China. Then China and US. US is not anywhere close. You try to take any paper in science, nature or something. Do you know when China has first got their PhDs? Anyone? Not bothered. There is not a single PhD in China till 1978. PhD does not exist. And when we were PhD students, when some paper comes from China, you just look at it and reject it. It will take only 15 minutes to reject. 90% of the papers from China in 90s, because I did my PhD between 88 to 93. China was nowhere. But now you see the ecosystem. In once, they are the leaders doing everything. So, a lot can be done in a decade. A lot can be done in 5 years, provided we have a direction. If a BTech students from IIT Hyderabad, what is the largest package that we got? 2.5 crores, right? When a BTech student can be hired for 2.5 crores, why not the top PhD student be hired, or why can't they produce? Because the problem is our ability to convert knowledge to wealth is not honed up. Elon Musk might have $1 trillion now, which is 3 times the GDP of Pakistan. And in Hyderabad, or in entire India, till 2007, there was not a single billionaire. But now, Bombay is the capital for the billionaires in the world. And in Hyderabad alone, there are 19 billionaires. We are into a developing mode. But there also need to be a change in the way things are being done. 5 years from now, in 1990 or 2000, 2010, 2020, 2026. 2026 is a golden era for Indian science because we have freedom. We can think, we can work, you can travel, and there are institutes like this. This institute did not exist till 4 years before, although people say that this was born in 2008 and 9 or whatever it is. About 4 years back, there are only 3 academic buildings. Now there are 35 academic buildings. As our Professor Muthiar is saying that 1,500 crores were turned out by the startups, and the support that IIT gave is about 10 crores. So I think she's there trying to show me 5 minutes. Now my lecture started or did not start? Nothing started. Because I thought that 11 o'clock, these are tough people. No, I will have to say something, otherwise. So drug discovery, earlier, who will develop drugs? A pharmacist or a chemist will develop a drug. Usually, who are these chemists? They will try to take the plant extracts, do the isolation, columns will be there, characterization and the structure function relationships. That's all. Things are so nice. But then these things have got complicated because of the entry of an unknown foreign body, that is biologists. Because till 1800, drug discovery used to have 40 million, 50 million, $100 million, and then 1990, $200 million. When the biologists entered, the cost has increased quite a bit. And then they wanted to know the mechanism of drug action. They wanted to know what is a receptor. And for that, you need to know the structure of the receptor. Can you take the structure of a receptor under the physiological conditions? No. So you have to crystallize the protein, take its structure, which is very expensive. So then there are many things. Then this is now taken by computer scientists, a good part of that. So let us try to see that this drug discovery is something that is happening and things are changing. I'm sorry, there is some problem with my computer. There is research that can be done with drug-oriented type of an approach or a disease-oriented approach. That is, you have a molecule which shows some therapeutic effect experimentally, and you can try to do the analogs of it. You can make a library of these compounds and then find out that by changing some substituents and altering some scaffolds, you can increase the biological activity. Or you can have a disease-oriented approach. You can try to look at the biological maps, and then from there also you can experimentally get the drugs. Computationally, if you believe that there is a model called lock and key model, that the protein ligand interactions or drug receptor interactions, a small key, small molecule is a key and the receptor is a lock, you can have a structure based approach or ligand based approaches, and many, many things are there. So there are people who are working on it. So there is a very well known thing, structure based design and ligand based design. So if you don't know ligand and structure, you need to do experiments, and if you know structure and you don't know ligand, you can have a structure based approach. If you have a ligand most of the time and you don't know the structure, you can have a QSAR and analog based approaches, and then many people have worked on this, and chemists are in the forefront. And then there are people, especially in the Eastern Europe, A.T. Balaban and other groups, they are very good in mathematics, and they developed some graph theory, many other QSAR equations. So there are many other approaches which are there, and I will very quickly go through it. most of you are from biology, right? How many of you are from biology? Oh, okay. How many of you are from engineering, AI? Oh, this is interesting. Okay. Usually, a cross-disciplinary science, somebody told me that you do AI and biology. Whenever you go to biology, you talk about AI. Whenever you go to an AI conference, you talk about biology. But now, this is a very interesting group. I can either talk about biology and AI, I talk about politics, which will be useful for everybody. So, now we will go back to this. So, this is a molecular representation, right? The different molecules can be represented in different ways. Because how do you represent a molecule? Molecule will have a nuclei and electrons. Nuclei, even at 0 degree Kelvin, although Professor Murthy is saying that I will freeze the molecule at 20 Kelvin, no, they will not be freezing. Even at 0 degree Kelvin, there is a 0 point vibration energy, right? So, you have the molecular structure, and then you have a one-dimensional, two-dimensional structures that are there, and there are somebody who wants to do computers, but computer will not listen to these things. They have only a Boolean logic. So, you will have to make a vector with 0 and 1, that is a bit vector, or you can try to represent with an alphanumerical string like Smiles notation, and there are many other ways of representing the molecules. So, but which molecules are similar? This is a very interesting thing. Chemistry is an interesting science. Okay. For example, all of you know functional groups, right? +2 something. If you take water, which is a universal solvent, and we all need it, that's absolutely essential. And if you want to substitute one of the hydrogens, what is the functional group which is very close to that? Maybe a methyl group, right? If you try to take the water, you substitute this one with a methyl group and you will have methanol. When somebody administers that, what will happen? It's toxic. Most of the spurious deaths are due to the methanol thing, right? And if you want to substitute methyl by another group, that is an ethyl group, right? So, if you substitute this by an ethyl group, there will be a big queue. Lots of people will be very interested, and then we all know the impact of it. This is much more valuable than water for most of the people in youth. But only later they realize that water is better than ethanol. That's a different thing. So, you will have an N-propanol. So, NC3H7OH. This also has, this is just an analog of that. This has 1670 times more impact than what ethanol gives. So, you have to be very careful in diluting at a proper concentration to get this divine effect. But if you do some ulta seedha in your calculations, you will go just reach the God, right? So, we have to be very careful. And then isopropanol has a different property. So, now if people think that similar molecules have similar property, where is the similarity? In drug discovery. And also, he has a problem, no problem, right? When I am moving here, you want me to stand like this? No, very good. No. So, there is a problem that there are some molecules which are dangerous, some molecules which are good. You have sodium, which is explosive. You take a small knife and cut a small piece and put it. We used to do it when we were young. At top, it will be there. If you take a big piece, then the bigger problem will be there. And then sodium is explosive, definitely not a very friendly thing. But chlorine was used as a toxic gas to kill people in First World War. But when you bring sodium and chloride, what happens? That is chemistry. This is also chemistry. And we all know that we require potassium in our life. Carbon is absolutely essential. Nitrogen is very much essential, right? Absolutely, they are very friendly. But if you bring these two fellows together, most lethal compound, right? So, how chemistry operates, how biology thinks are very different. If similar molecules will have similar properties, no. I always compare that molecules like human beings. If I wanted to know who is Amitabh Bachchan, I will get his photograph. I will put who is Mahatma Gandhi, I will put his photograph. I will put Nathuram Godse, I will put his photograph. Sachin Tendulkar, his photograph. But just by looking at properties, can we look at their behavior? Difficult. So, this is also like that. You have 8 molecules which look very similar, but if you look at volumes and surface potentials, they have one particular pattern. If you see hydrophobic and polar region, they have yet another pattern. Hydrogen bond donor potentials, they have a different pattern. Hydrogen bonding accepting potential, they have a different pattern. Molecular electrostatic potential, they have a different pattern. So, the chemistry is very diverse and it is very difficult to predict what happens. Whereas, if you look at biology, they are mostly consist of proteins, which are with 20 or 22 naturally occurring amino acids with the different peptide bonds, and you have nucleic acids, you have RNA, you have DNA, maybe you have quadruplexes, and you have carbohydrates, you have lipids. They are highly complex but not very diverse. Chemistry is very diverse but not very complex. So, we need to understand how chemistry and biology will come together. One is an observation science and the other is an empirical science. Okay. So, computers have entered into picture. I just wanted to say that I was trained as a theoretician. Oh, I changed my fields. I was a theoretical chemist because I used to hate organic chemistry and biology because I was trained, because I wanted to avoid that. But now I am in the Department of Biotechnology. So, you may think that you want to hate them. Now, I will talk about biology, genomics, although we are neither experts nor we are interested in that. But somehow we have to do it because there is money in that. Because drug discovery is very important, aging is very important. So, we publish lots of papers, right. Looking at the strategies for drug design, you have an inhibitor design or benchmarking of different things, non-covalent interactions, drug metabolism, molecular dynamics, virtual screening. Why do you publish papers? Unfortunately, you take PhD students. And these PhD students want papers. And when you join, you require only nothing else is there in the world. You, your PhD students, your papers, your awards, and that's why I got every award in Indian science. And afterwards, if somebody asks you, what did you do? I published so many papers, I got so many degrees, so what? Will something happen to the world if you do not exist? Nothing will happen, or something will happen. It all depends on your perception. On a different side, I can also say that yes, I have made these 5 different contributions or 10 different contributions in my area. If I have not born, these would not have been born. But the thing is, if you ask G.N. Ramachandran, what did he do in his life? He can say it in one sentence or in one graph. If someone says 1000 pages to tell what they have done, probably they have done nothing. If you actually see G.N. Ramachandran, he was one of the pioneering researchers when he was in Chennai. He went to MBU, IISc, and his research died. So, please do not think that when you go to a premier institute, you can do better research. Some of the great research that G.N. Ramachandran has done when he was in Chennai. So, we can publish papers and then we can try to look at that is the methods, and then you can try to take different targets, because I know that this is just to show that I have done some work. Otherwise, people will say that, okay, you are talking only politics and you have not done many things. So, you can publish papers, there is no doubt about it. And the thing is, in the computational drug design, you have QSAR, molecular docking, molecular dynamics, but the fundamental limitations or they are dependent on human expertise. Who is more intelligent? Can you compete with ChatGPT in writing an essay, or writing a code, or giving an ideas, solving a problem? But with ChatGPT is better than humans. So we will come to this. So there is a disconnected linear workflows which are there at each stage, and overwhelmed by complexity. Because if you want to do drug discovery, what you have to get? You have to just get one molecule which will do the action. It is similar to hunting for if you want to get a best singer, you have to get only one person, right? But the chances, if you want to have a best dancer, you can have a competition and then you can do it. But if you want to have a best drug molecules, the complexity is very high. And many times people will make a molecule by the time disease is gone, and they are so upset. So that this is like a drug development cycle is like this. Most of them will have a valley of death. If you see the research and development are very different. Drug discovery research will have your preclinical trials, animal models, in vivo, in vitro studies, and development will have phase 1, phase 2, phase 3 clinical trials, and then survival, phase 4 clinical trials that are there. This takes about 10 to 15 years. And the amount of money typically on a given drug molecule is close to $2.5 billion, which is much higher than the MHRD budget that we have. We also have to put it in a perspective. So if you don't put that, is it possible for you to develop a drug? Tough. But if you want to develop some drug for some skin and some other thing, you can probably on average is $600, $700, $1,000. Say, sorry, not $1,000, $1 million, right? So there are different things which are there. And even when you develop a drug, product launch will take some time, then still you have to invest money to become a successful model, you have to wait for some more years. And once it is successful, a successful drug will take care of the company for decades. That's why there are only unipolar world. There is only a Pfizer. There is only one Sanofi and Avanti and other things. And in India, most of things, when they are trying to say that they are doing drug discovery, they go up to a particular point and then they sell it to different people. Because end-to-end meeting will be difficult, because most of them eventually will get into the valley of death. It's tough, because if you want to start a clinical trial, you have to invest a lot of money. Some of you have heard Krishna Yella's lecture. Do you know who is Krishna Yella? Oh, then it's good. Ignorance is bliss. Krishna Yella is somebody who developed these vaccines, and he and his wife got Padma Bhushan for this, and then he has shown that how the vaccines can be developed very quickly. One of the reasons is these drug molecules will fail in clinical trials. Why do they fail in clinical trials? Nobody knows. What is the reason a molecule fail in a clinical trials? Absolutely no idea. There is no serial thinking or a theory which can be employed to know the answer. But you can collect the data, and using a machine learning approach, you will be able to get an answer. That's what we have done about a couple of years before. We published this paper, assessing machine learning approaches for predicting the failures of investigational drug candidates during clinical trials. So the data should speak. The knowledge that we have should be in a way that you will be able to get some information. The data should be converted to knowledge. This is possible only by machine learning. Because we have looked at, some of you are interested, they can go through all the papers which are there. And similarly, you can try to develop a model. So this is also published to you, that how do you get a model for the blood-brain barrier? There are so many models. There are hundreds of papers which are there. Probably this is the best that we had, because we are able to deal with that with a larger data. What I mean to say is, things are changing now. Our capabilities are changing. And you cannot really expect to do the type of research that you have done during your PhD, even though your PhD is only 4 years before. The whole world is very different before 2023 March and after 2023 March, because 2023 March is the first announcement of ChatGPT. And then Perplexity. Who is Perplexity? This Arvind Subramaniam. This fellow, a graduate from IIT Madras, electrical engineering thing, he is probably the youngest billionaire in the world. He is just 32 years now. They developed Perplexity against all the odds. And the type of knowledge that they have is only 4 years. So if a old guy like me want to talk to you or talk to the students, we also first acutely be aware of our limitations and then understand the reality. There was no point in time I said that why do we need PhDs and why do you produce these things, right? But I will go to one more extent. Do students need teachers? I don't know. Do professors need PhD students, or they can do better by employing some chatbots? Not only for theory, for experimental also. Okay, I wanted one student to collect experimental readings, right? Every half an hour for 4 days. So I have to have at least 2-3 students, and sometimes they will sleep, they will be hungry, they will be doing something, they are on phone. But this chatbot fellow will be more punctual, right? If you know how do we do it, robotics and automation. So things are very complicated. I don't want to scare you, I just wanted to tell you that you can think differently. And you have to think differently. Because the paths, there is a book by Marshall Goldsmith. The title of that book, I recommend you to read it. What brings you here cannot take you there. The essential meaning of that book is you use some methods in your life to reach a particular stage. If you do exactly the same methods and then go in that path, from this stage to the next stage, you will find the resistance. You will have to change your path. The type of path that you have to become a faculty, from a faculty to a senior faculty, from a senior faculty to an established faculty, probably you will have to change. I am very, very interested in this year's Nobel Prize. Think about creative destruction, which is very nice. So if you want to allow the new things to impact positively in economy or knowledge or to the development of a nation, you need to take away the existing thing. Okay, some new fan has come or new table has come in your house. You have to take the old table. You cannot say that I will take the old table and new table and it will not be working. So most of the time the resistance for the change comes with people who are practicing and obsessed with the old style of working. So when we come here, it will be not a thing that I can teach you some biology or artificial intelligence or whatever it is. We need to think. Take the time. Each one of us, each one of you, oh, we are going in a path. Is it okay? We can do anything in our life, but we cannot do everything. So we have to be very, very clear that what we have to do and what we cannot do. And I always say that there are two things in life. One is important things, which is very, very, this is the only thing that will count when you retire or when you look back after 1 year, what you have done, these are important things. But the second thing is essential things, which you cannot postpone. Attending a meeting, somebody will come, there is that. These essential things will be completely useless. After 1 year, when you look back, what did you do? None of these essential things will figure in your yearly or retirement plan. But we end up doing all the things which are essential. We will end up having no time for important. So it is something that we will have to have a balance, that what is important and what is essential. So you can ask different questions, and there are different technologies which are coming up. I don't want to Drug repurposing is another area, because you are not from biology, I will go through it a little bit quickly. So, what we have done is, we try to develop a software. This was so bad for me personally, because I was a very established scientist. I published lots of papers, and then I wanted to develop a software, because earlier we are buying the software and then using it. So, this idea that I got in 2004, but I did not want to do it till 2011. In 2011, I got the Shanti Swarup Bhatnagar Award. In 2004 also I got the Swarna Jayanti Fellowship. I was so lucky, because somebody thought that I am doing useful things. So, that is a different thing. So, they gave lots of money. So, when they give money, you can do fundamental science. Support for science is very important. So, I started in 2011, and we had a huge group of people, and we published in 2017 a paper which has about 54 authors, all are Indian authors. It is a result of about 5-6 years of work. Then we tried to publish something in 2018 with the thing. This is a software that we want to develop, and I just wanted to tell you that this is a drug discovery software that you can develop from scratch, and still we have difficulty to make it accessible to everybody, because the people who want to use it should be more technically savvy. They should be put their galaxy in their platform and then try to use, and most of the people do not have the patience, including us. So, I will try to skip this, because there is not much of a time. So, one of the things that we have done is, first time we have structurally classified the molecules into different structures, and we gave every molecule an Aadhaar card. This was also published in 3-4 papers. So, the molecule, we can see that to which class it belonged to and which cluster it belonged to. We gave an Aadhaar ID for this molecule, and then this is a compound library which was published some time back, and there are different modules of this software which were published, and they are available. And we are very happy that we are able to do something, but this is not something which is very interesting for the students. Students want to publish papers with a high impact factor journals and multiple papers. But if you develop a machine, or if you want to develop a software, it will take 5 years, 6 years, and you may not get paper. So, most of the time a head has to take a decision and the body should move, right? But in India, the tail will take a decision and the whole thing will move. So, this is a problem. What you have to do in a system or in a group will be decided by a PhD student. That is fine. But when you are a leader, scientific leader, you also want to achieve something in your life. So, many of the times we are not very clear of what has to happen. We go with the flow, and somebody else will tell you that you are successful, and we are very happy. That guy has no idea on what basis they say that you are successful. Somebody else will say that you are a failure. There is no idea why you are a failure. My postdoc boss said that research is very simple. They will ask you to fight. They will give you a sword, and they will put a blanket so that you cannot see anything. They ask you to fight. You fight for 1 year, and then they will take out your mask, and say that you are successful. You don't know why are you successful. And somebody will say that you are a failure. You don't know what is a failure. So, most of the time research is like that. So, we have to take a very clear approach that the parameters based on which they judge are very difficult. So, you yourself will know, and many times, although you know that you are successful, the society will say that you are not successful. Do not worry. Although society, everybody says that you are successful, you may know that you are not successful. Listen to that. And in both cases, self-assessment, self-judgment are absolutely important. So, now this generative AI has come. Many of you are from computer science and other things, right? We started with neural networks, which is there almost for 40 years. Actually, University of Hyderabad is one center which was created in 1984, that Center for Artificial Intelligence. Probably this has started giving BTech after BSc. BTech 3-year course that they have started in University of Hyderabad, because I did my PhD from University of Hyderabad. So, we have all these batches, artificial intelligence center. We used to joke, natural intelligence, artificial intelligence. Oh, this guy is an artificial guy. 5 minutes. Thank you. I should not be looking at you. Then what happens? Okay, the generative biology has come from prediction to creation. The encoder decoder models which have come, and then pre-trained transformers which have come, they become very important in all other areas. I just wanted to tell you that our group has done some research in different areas, because what is the reason? The tail will decide, the whole body will move. Somebody will be interested. I will develop a database. Okay, develop a database, publish a paper, get your PhD. I will do something, do that, publish, do that. But still we also should be interested. But this is the best of its kind database. In Oshadi, this database gave the pan-India database of medicinal plants covering all the states as well as the UTs, and there is follow-up work that is also being done. This is the first of its kind, that is the best of its kind, this is the first of its kind in Northeast database that we have created, NIM PDB. So, can I take 5 minutes? I will give you a chocolate, okay? Fine. So, the disease you can see as a perturbation to health, but most of the time the medical care and the health care are seen differently. So, I will try to very quickly tell you that we are interested in aging, especially with Dr. Sandeepan, because he is a circadian guy, and then we are trying to look at the aging. Chronological age is a simple passage of time, and biological age is the rate of entropic decay within the system. So, we are now trying to look at the differences of the aging, the immunological aging, biological aging, chronological, psychological, cellular, and agiotypes, what are they? There are people who may be 60-year-old, but they are almost like 80-year-old when their cognition and all. But there is somebody who is 80-year-old, they are like 40-year-old. So, what are the parameters? How do you characterize them? So, these things are becoming very important. Many companies have come. Now, looking at the biomarkers, biologics, long non-coding RNAs, your telomerase length, many things are there. So, there is from monolith to the distributed network, there is a lot of focus in this, and one of the PhD student, I have absolutely no idea what she is doing, but her topic is decoding aging using sustainable AI. So, better that you take a PhD student, you say that I know nothing about it. This is your problem, you do whatever that you want to do. Because I have been 32 PhDs have done PhD with me. I used to earlier think that their problem is my problem. Usually what happens is their problem has become my headache. My problem has become their headache. So, it is better to detach. You take a PhD student, you do whatever that you want to do. And then you just you detach yourself from this. So, this girl is doing something, something will come out. And one more guy had talked about cellular heterogeneity. This is a very interesting thing, that the heterogeneity in the cellular system is a nonsense for many of the biologists. Whenever there is a complexity, you would like to avoid it. But this guy would like to take head on to see what is it saying. Like all of you have a joke, right? You lost your gold ring when you are walking in a bush. And when you come back, you don't want to search it in the bush, you search it in the place where there is light. Our research is also like that. Sometimes when there is a complex problem, we know that this has to be done, but it's too complex, right? How do I get my PhD? How do I get my promotion? Things like this. So, this cellular heterogeneity is something that if he survives for PhD, something will come out. And he is a computer scientist, and then looking at some app, chatbots and other things with mental health. He will try to look at the conversations of the people and their voice. And the voice will be lot of conversion to speech will be there, and then they will take some keywords, and from there they will be predicting their depression and things like that. So, mental health with generative AI, when I ask people to look at what is an interesting problem, all my students are saying that depression, mental health, suicide, it's okay, if you are interested you do that, and then what is the biological link with this. So, this guy is also CNS disorders and trying to develop an encoder decoder model using agentic AI for this. And I told you that there is a database that we have developed. This MTech student is trying to develop the phytochemical diversity of the country and mapping on the geospatial thing. So, these are two different things, and then we will be able to come up that what are the factors to identify the plant secondary metabolites in the geospatial, depending on the geospatial thing. And we are also looking at the pharmacovigilance in Ayurvedic drugs, because I believe that each student should come up with something, and probably at the end of the day they also should be able to get a job, and these are interesting areas. So, I will try to quickly go through, because this is somebody is interested in doing long. I used to have lots of computer power, now I do not have much. I have only some power, artificial power, not real power. So, IIT Hyderabad, I do not want to say, because she has given only 5 minutes, and you know this, you all know that we would like to, we do not want to call it as Indian Institute of Technology Hyderabad, and our director would like to see it as inventing and innovating in technology and humanity, for humanity or whatever. So, we are standing first in the second generation IITs and will be striving to join the first generation IITs. This is what I have made about 5-6 months before, but now we have already achieved. We are now in NIRF ranking is over Guwahati. We are very proud. I do not know whether we should be proud of it or not. We are now trying to target whether we can take over Kharagpur and Kanpur. These are our low-lying targets, and Hyderabad is coming very good. And this is our Department of Biotechnology that you have to come and then see. This is an old photo, but now you can see that this part is biotechnology and that part is biomedical engineering. It's like a chromosome shape. These are the interesting students, and they think that they will come and then do whatever that they want to do. I do not disturb them, and something will come, and I take all the credit as an Indian system that is there. But this is what was my group when I was in IICT, then I went to Northeast. So, these two are the Northeast groups which are there. This is all because students are working, and it will help us to go and then talk about it. But most importantly, some big questions that you have in mind, it is only because of the students and colleagues that you are able to even dare to think about it. And another thing is, many times you are in one particular branch of science, you get a fundamental thought in a completely different area. Because you try to curb that, because you can't do that, right? But now things are different. It's important. If it is biology, it is so complex, no biologist can do it. An engineer can do it, physicist and chemist can do it. If it is physics, maybe a biologist can do a better job or something like that. So, we have to dissolve our individual identities that I am this and I am that. We have chatbots, we have Gemini, Perplexity, ChatGPT, everything is there. But more importantly, we need to have the scientific inquiry and the power, because the hallucination is very much there. Most of the time, when you get an answer from these generative AI models, they are wrong, incorrect, absolutely ridiculous, but they have an audacity and the responsibility to give an answer. But you have to extract the right answer. Actually, we just published a paper last 2 years before, just with ChatGPT. Then it came in a journal of, it's ACS journal, JCIM. We asked the same question for the material design. We know whether the answer is right or wrong. You ask the question with soft prompting, and if you know, you use this technique of soft prompting, in 14th or 15th iteration, you get the desired answer. So, there are many things which are coming with Gen AI and agentic and foundation models, and things will be very different. If you know nothing, even that is an advantage. Ignorance is bliss, somebody said that. So, please do not think that I am intelligent. No, you need not be intelligent. I am skilled, you need not be skilled. What all you require is, you need to have a passion, you need to have an attitude, you need to have the perseverance, and you need to develop the ability to ask the right questions and try to decrease the hypocrisy to as low level as possible. I just wanted to say that the most important thing is India starts with cognition first theory, and we have to believe in Trikarana Suddhi. That is, what is Trikarana's Manasa, Vacha, Karmana. What you think and what you say and what you do. If you can decrease the gap between these three and ask the right questions, irrespective of the fact, then things will be better. Sorry for talking a little bit. Thank you very much. I will give you a chocolate, right? So, oh.
Interesting talk. So now the session is open for any questions.
Talks will be interesting when you don't speak science. It is available, yes, it is available. Anybody it's available, academician, non-academicians, anybody can use it. Only thing is they will have to adopt to this local platform, because MPDS does a large number of calculations, and this is now located in Jorhat, and if you fire a job, it will tax that particular thing, but you can download all the things. Everything was deposited in GitHub, and you can recreate everything, and you can write to us, we can help you to recreate that, and then you can use it, and then you can develop your own small codes to improve that. Yeah.
Sir, you talked about Aushadhi, that is a database what you have created for the medicinal plants. So either the plants, because basically we are from Ravi Shankar Shukla University, Chhattisgarh, and there we are having a plant list of 1500, more than 1500 plants. And out of that, when we go for the data of these plants, we never find any data related to that, but they are listed there. So either
You have seen the Aushadhi?
No, actually, because that FHRL initially they were having with some plants, but literally from the silver platter database it was removed, and now we were searching for some reliable. So just you told me about that. So I am very much interested related to these plants have been considered for that, which are officially been given by Medicinal Plant Board from the Chhattisgarh.
I think they are considered. Close to 7,000 plants were there, and I am sure that these plants will be there. If it is not there, we can add.
Thank you.
So I am also a Dean Research, Sponsored Research and Consultancy. I will be very happy if we can do something with any of your institutes. The collaborative research. Chandrasekhar Sharma is a very active person, and this is life sciences, and I am in the vertical of artificial intelligence. Chandra, Krishna Mohan is one of the persons. Krishna Mohan, Srijit and I, we will try to have one more conference sometime during the holy season that is announced. That will be announced, or that will be announced. And some of your colleagues can attend that, or you can also attend.
We now proceed to final scientific talk of the day, mathematics in clinical Panchatram Mariyappan is an associate professor in the Department of Mathematics and Statistics at IIT Tirupati. His work centers on applied and computational mathematics, focusing on computational fluid dynamics, numerical methods for partial differential equations, and scientific computing, particularly high performance and GPU accelerated techniques. He completed his PhD from IIT Madras, followed by postdoctoral research at Fraunhofer Institute of Industrial Mathematics, Germany. Dr. Mariyappan has received several recognitions, including the DAD Research Ambassador Award and the Best Faculty Award for Teaching, highlighting both his research achievements and the commitment to excellence in education. Now we invite Dr. Panchatram Mariyappan to proceed with his talk.
Okay, thank you. Thanks for the nice introduction. Thanks for the invitation to the Coasting Institute. So today I'm going to talk about some not more mathematics, because I know like you are from how many of you like mathematics first of all? Okay, there are few. Okay, so we'll not talk much mathematics, but we'll just give you some glimpse of the mathematics where I'm using these AI tools and other things, especially the PD, etc., for solving some of the clinical problems. So we have, so the title, this is my reference. Okay, so I'm just covering some of these from these three papers mostly. You can just have a look at it later if you want. So one is in Nature Scientific Reports, another is in International Journal of Computer Assisted Radiology, and one is in PLAS ONE, and few more are there, but I didn't list everything. So the idea is that like we have, so the main thing which I'm going to talk about is the cancer treatment software which we developed in the last, because as he was mentioning, like developing the software will take a long time. So we developed like last 5-6 years we have developed, and still we are developing with artificial intelligence, etc. So the one of the problem for the cancer is that mostly the liquor drinking and other smoking, etc. So I'm going to talk about few more cancers, but first I will concentrate on one cancer, and then the same idea we can extend it for other cancers as well, which is called liver cancer. So common liver cancer is HCC, which is hepatocarcinoma. So that cancer, like we have the liver cancers are there, and the standard therapy usually they go for is the surgical treatment. Okay, they go for the surgical treatment, but the best one is transplantation. If you do the transplantation, you get it, but most of the time you won't get adequate donors, and they go for the surgical treatment. Surgical treatment again, like 75 to 90% of the time, that will be in a complicated position, so they can't do that properly. The idea is we want to limit the cancer growth. For that, the people use the cancer treatments like radiofrequency ablation or microwave ablation or cryoablation or irreversible extraoperation, and even like focused ultrasound, laser, etc. But here one more problem is there. The doctors, the oncologists, they call us radiologists and oncologists, they are not experienced. So if they are not experienced, what is happening is that if the doctors are less experienced, either they will kill good healthy cells, more good healthy cells, or they will leave some good, some dangerous cancer cells also without properly killing it. So, so if there is under treatment, again the cancer cells will reoccur. If it is over treatment, again it will be leading to the death also, okay, immediately. What we developed is we developed a minimally invasive cancer treatment guidance with the help of the doctors and the radiologists and engineers, etc. So where we want to help the interventional radiologist in such a way that they choose the correct parameters using the artificial intelligence, etc., so that they go for the correct treatment, and then they can make the treatment properly, and this will be guided by them, and then they can do it. So here what we did is, like I'll just show you one quick example of that. This is the radiofrequency ablation. So let me just see. So this is the radiofrequency ablation where you have a treatment.
the skin, enabling electrical current to pass out through the patient's body. The patient is slid into the scanner, and with imaging guidance, the physician locates the tumor. Once the tumor is located, the needle electrode is guided through the skin and advanced to the site of the tumor. When the needle electrode is in place, tiny umbrella-like wires advance out through the needle to set the position and to widen the surface the electrode current affects. The electrode passes electrical current with a range of radio frequency waves, creating heat around the tiny wires. The heat destroys the tumor, leaving normal healthy tissue unaffected. During the procedure, the patient may experience a mild sense of heat or pain.
So it will be repeating again. Okay. So here what we try to do is that we have to mimic this model mathematically, and then we have to use the AI tool to help the doctors, because we have to virtually, means it is called a digital twin. Okay, in the AI term it's called digital twin. That we want to replicate it, and then we have to train the doctors, or we have to train the, so they don't need to do it to the patients directly, but instead they can use this tool to get the training, and then they can go for the thing. And not only that, it is useful for the well experienced doctors also, where they can keep that as a side tool, and they will understand like what kind of parameters they have to tune it. Okay, the parameters we'll discuss. So what I have here is like this is the cancer treatment, where there are different types are there, okay, microwave, etc. So what we have to model is that for our clinical, means the clinical AI treatment, what we have to model is that we have to first of all get this CT scan images. Okay, once I get the CT scan images, I have to replicate the similar kind of things in the virtually. Means if it is a liver, I got to virtually create the liver, which is from the patient directly. Okay, if it is a lung, again I got to create kidney, means kidney we got to produce it. Okay, not only that, we got to do the vessel. Okay, the blood vessels like hepatic, artery, portal, etc. That also we got to create it, and we got to find like where the tumors are there. Once the tumors are found, that also I got to replicate in a digital twin, and based on that, what we got to do is that we got to go for the treatment protocol. The treatment protocol will be different. It's patient specific, and it's also many specific parameters are going to come. So for example, this is a typical 5 centimeter protocol in the radio frequency ablation, they call it as. Means you see that there is a needle coming. For example, this is the top one, you can see that there is a needle is there. That needle is going to be inserted inside the liver through our hip side. So that will be taken, then there will be umbrella is going to come. That umbrella is going to be, that needle umbrella is going to produce the heat, and it's like a pen. Okay, the pen kind of thing. So it's going to be pushed little bit, then it will be 2 centimeter, 3 centimeter, 4 centimeter, 5 centimeter, up to that it will come. So mostly this is for 3 to 5 centimeter treatment. They used to, the size of the tumor they used to treat it. So in this they have a protocol. So 2 centimeter they have to generate it. Means 2 centimeter first they have to keep it until that is giving like 95 degrees Celsius, for example here, and different devices will have different settings. For example 105 degrees Celsius, then we got to produce the similar kind of things. So in that case, what we got to do is that we have to generate a similar kind of thing. So once the 2 centimeter is done, we will keep it there until it is reaching the target temperature, let's say 95 degree or 105 degrees Celsius. They will keep it until 30 seconds. So 50 minutes minus 14.5, so 30 seconds they have to keep it there, so that the 2 centimeter will be killed. Then they go for the next one, okay, again 30 seconds like this, and then for the last one they will be keeping 10 minutes or 7 minutes depending on the needle type, etc. So here we got to mimic the same thing using our clinical AI treatment. Okay, clinical AI treatment also have to do the same thing. So this is the generator, RETA power generator, okay, RFA Starbus generator, that produces this exactly the same thing, whatever I explained that will produce that, and there are thermocouples available here. So you can see that there are thermocouples, 5 thermocouples will be there, that will be measuring what the temperature is there inside the liver or tumor, etc. And that profile also we get it. Okay, that profile also we got to get it. So we got to train our model in such a way that that is also taken care into the account. And not only that, so different people will be having different parameters. So somebody will be having high BP, somebody will be having low BP, somebody will be having fever, etc. So then that also we got to take into the account in that. So therefore we call it as a patient specific parameter and device specific parameter. If I change the device, then I got to change the model. If I change the patient, BP level, everything we got to take it. So that we got to take it, and this is different one. This is for the microwave one. Okay, similar kind of settings we got to do that. So here, what we got to do is that we got to the challenge here is as follows. For example, I say like 5 centimeters, so totally it is mentioned as 15 minutes. When there are vessels present, what is going to happen is that sometimes it will go even 1 hour, that treatment will go. Okay. For this 1 hour treatment, if I just try to do that using the standard softwares which is available, it will take 7 hours, 8 hours. But the treatment total is going to be like 15 minutes to 1 hour, and it take like 8 hours to predict it. There is no point of having that software in my clinical setting which we cannot introduce that. For example, this is similar to what we are having in the weather prediction. In weather prediction, what we are trying to do is that today's weather I got to predict whether it will be rain or not rain, or whether it will be a flood will be coming, etc. We got to identify. So if my software is going to predict that after 10 days, today it is going to be flood, there is no point because I cannot evacuate the people. Same thing here. So I am just trying to find a software tool, the clinical AI tool, which I want to generate it in such a way that within few minutes, few fraction of second, it can generate it, and then the doctors can immediately change the protocol, or they can change that device settings, etc. They can do it. Okay, so they don't need to wait for a long time, etc. So what we got to predict is that we got to mimic everything what the doctors are doing using this clinical AI. Means they got to take care of the patient specific, they got to take care of the liver, they got to take care of the vessel geometry, etc. They got to take care of it. And apart from that, we got to say like whether the cells around the cancer cells are going to be died or not died. That we got to generate it. So for this, one such model is called the partial differential equation, is the heat equation. So if time is there, I will just tell you in the end of the lecture like how we generated that model, etc. So in this case, so these are the protocol. Okay, so power input I have given, protocol I have given, RFA generator, RFA needle, if it is microwave generator, and treatment. So this is taken in one of the hospitals. So this is done as a project with various university hospitals. So one sec, I think the previous slide is missing. Yeah, so we developed a software tool. Okay, it's this is the software tool we developed. So in this software tool, I will just show this website for that, which is called Clinic Impact Project, and we developed a product also called Clinic Impact Product, which is a standalone which can serve in the hospital itself. Means near the CT scan bed, we will keep that monitors and then computers, which is a desktop computer where the GPUs are installed. Okay, in the GPUs it will do that job, and then it will produce the output for you. So we did all these things, like we did the image processing, means from the once the CT scan images are provided, we take the segmentation of that liver, etc. And we did the needle insertion, that also we do that. So there are three types of things are there. Okay, we'll see that, and we simulate it and fine tune the parameters, visualize that, and then we just validate against the real cases also. So that we develop, and it is like we accept all these parameters and then we developed it, which is predicting the lesion. And this is developed by European Union Commission project, which was headed by Fraunhofer FIT in Germany, and there were medical universities and companies were part of it. I was part of this company called Numa, which was 3.7 million euros, which we developed in 2014 to 2017. So the the University of Leipzig and Medical University of Graz and Radboud University and the Turku Hospital, which is Werner Schumann. So those hospitals were providing the patient data to us, okay, all the clinical images and what is the temperature of the patient, what is the vessel diameters, everything they provided to us, and they provide the CT scan images. And Medical University of Graz University of Technology in Austria and Aalto University from Finland. So they were developing the clinical part for segmentation of the needle, segmentation of the liver, etc. And I used the clinical AI software development for simulating and parameter estimation, etc. as a mathematician in this company. So the software which I showed earlier, that this is the software tool, okay, which takes care of everything. So the idea is that they upload, this is a open source tool for MITK, okay, MITK software. software tool is there. So based on that we built, on top of that we built that. So this, once you upload that images in this software tool and you click one button, automatically it will just segment that liver, it will automatically segment the vessels, it will automatically segment the lesions, I mean the tumor also, it will generate that. So there are 3 stages are there, I will show it in the next slide. What is having is that there is a, before the treatment we got to get the images of the patient, and during the treatment we need to get the images of the patient, because I need to know like where is the location of the lesion and also tumor, as well as the where is the needle is inserted. So that details I require. So that time we take it, that is called peri-interventional. So this is called pre-interventional, means like we take it before the treatment, peri-interventional is during the treatment, and then post-interventional also we do it because we want to validate whether whatever our digital twin and the simulation which we developed using the clinical AI is matching with the real protocol which they followed and then matching it. Okay. So for example, here the green color one is the really treated outcome of the patient by the doctors which they provided, and the one which we have it in the blue color, that is called the simulated one, means our digital AI or the clinical AI which we develop, that is going to develop the answers for that. Okay. So this we developed, and it is we tested it around 100 patients for this one, and then we published the papers in the Nature Scientific Reports, etc. So these are the workflow which is happening in this software tool. So we collect the data manager. The data manager is all the images, pre-interventional images, post-interventional images, and peri-interventional images, and our tool takes care of the segmentation. So we take automatically it will take the segmentation of the tumor, vessel, and then the liver also, and so we combine that as a digital twin. So the liver, I just combine that as a digital twin, and then we try to see like what is going to be the that is going to be the input for my mathematical model, which will generate a volumetric mesh, because I don't require a complete liver for me. This treatment is called loco-regional treatment. Near the tumor and near the needle there will be a lot of amount of heat will be produced, whereas further away it is not going to be there. So in that case what we did is that we just made that domain as a little smaller, where the influence is going to be higher, where the negligence is there we just remove it, and that saved a lot of time. So then we were able to simulate that in the peri-interventional stages, where we collect the needle, virtually we generated the needle, okay, and then we just inserted the needle wherever the location is there. So exactly it will be translated and then kept it, and we take all the patient specific parameters like perfusion or temperature or the needle type, etc. We take care of it, and the protocol also, which kind of protocols they have it, and like in that video I just saw one tumor which is going to be there, and multiple, sometimes the tumor is going to be large. Still if they are going for this treatment, they call multiple ablation, means they treat it one location, and then they will take the needle and then they just change the position little bit, and then again they treat it so that they will kill larger tumors also. In that case they will go for some multiple cycles also. Okay, that also we got to take care of in this clinical AI one. So then finally we produce this the red color one, that is the simulated one. The digital twin is going to generate it with the clinical AI. And then we got to calculate that lesion. Lesion is nothing but the dead cells. Okay, the dead cells we got to compute it, and that we got to compare it. Okay, in the post-interventional, they will give that post-interventional segmentation also they will give, and that we got to compare it, and then we compute the values for this one. So here we applied many mathematical things so that we reduced a lot of time. Okay, one of the thing is like I don't simulate the entire liver. Instead, I just make smaller domain. Okay, and then I try to do that, so I saved a lot of time for that. And then all these patient specific parameter, needle parameters I have given, but I use the GPU computing and the AI settings so that it takes maximum 2 minutes for me. So even if it is a 1 minute, 1 hour protocol also, it can take maximum 10 minutes for me to see simulate that. So that then by the time if the doctors are completing, then they can do that. If it is a 10 minutes protocol, maximum it takes 30 seconds to 60 seconds it takes. So by the time they can just change that mind if they find that there is something is wrong going in that. And Then here we made some more changes where we developed the mathematical model. So usually when we want to compare that two things, what they try to compare is that we want to do something called volumetric overlap or dye score and sensitivity, etc. They try to do that. Once they try to do that, what they were trying to do is that they would try to regenerate the entire thing. But we used some of the mathematical technique. One thing which we always teach to the BTech student is called Gauss divergence theorem, which is relating the volume with surface. I have mostly the surface here. So using that theorem, I don't need to regenerate the entire volume because that computation is going to take a lot of time. I just used only the surface, then I just immediately calculate the value, and that also take a lot less amount of time. So maximum we have taken only 10 minutes for a larger protocol, and if it is smaller protocol, 2 minutes we have taken, and we compare that for 100 patients, and then we publish that in the paper also, and it's available and still they are functioning in some of these European hospitals. So this is the mathematical model mostly we have used, called bioheat equation, which is a famous equation since 1948 called Bend's bioheat equation. Which we have used it for generating this one, and for vessels we used the model of the Newton's law of cooling, and cell death model this we have developed with the help of Oxford University, where what we did was like this is something similar to the COVID-19 model. In COVID-19 we have a model called SIR model, susceptible, infected and recover model. A similar kind of model. So here what we have is initially we developed a 3-state model. So the 3-state model is like at any stage we have three states. The cells can be, the cancer cells can be either alive, or it is vulnerable, or it is dead. Means the cells can be alive or dead, or it is in the stage of moving from alive to dead. It is similar to the SIR model. It's like susceptible, infected and R. Okay. So R means either recovered or deceased. Okay. So the similar kind of thing, where we at any stage, if I give any population in this model also, what we have is that this S plus I plus R will be always 1. So it's a kind of a binary thing. Either this will be, either I will be here, or I will be here, or I will be here. Okay, so in this case I will be there. So same thing, if I take any cancer cells, either it will be alive or vulnerable or dead is going to be there. So A plus V plus D is always 1. Okay, then we changed it to, so V is nothing but 1 minus A minus D. So this we kept it, and then we simplified this model using this one. So this alive, vulnerable and dead, there are plenty of models available for this one. There are like Arrhenius model, etc. But we developed this model, which is going to be again a ordinary differential equation, system of ordinary differential equation, where the temperature which we get from this treatment for the bioheat equation, whatever I solve, so that is going to be the input for this one, and then based on that I will say whether the cells are alive or dead. Okay, so mostly if it is more than 65 degrees Celsius, already the deaths will be started dying, and accordingly this model will be taken care. So these parameters we have estimated, okay, using the again the AI techniques, and then we found out what is the best KF and TK, etc. So based on that we developed this model, and we used it in this one, and we identified that. So the red color ones are means that it is saying that D is greater than 99. Okay, if it is more than 99, then I am collecting the cell that is going to be like that is going to be the dead cells. That red color one is the dead cell which we simulated, and green color ones are the one which the doctors cause after the treatment they have provided. This is the correct one, and then we check that, and usually doctors says that if the surface deviation is less than 3.11, then that 3 centimeter less than 3 millimeter, then it is called as a good one. And similarly the volumetric overlap and dye score, everything is greater than 80% or 75 to 80%, then that is a good suggestion. So most of the time we got the dye score and sensitivity, everything like more than 90, and we were tried to calculate like what is the standard deviation, surface deviation, etc. we calculated, and most this was accepted in the clinical one, and the European Commission also rated our software as a 4-star software for that. And the critical thing here is that it was helpful for identifying some of the faulty devices. For example, one of the hospital, when we simulated and they provided data, there was some mismatch between whatever we compared the sensitivity, etc. And then we found that why that particular hospital is having that one. Then we asked them to provide this the temperature data, and the pulse which was produced by the machine, etc. What we did was we just analyzed that, and then I reverse engineered that machine and then tried to see that there was one signal was not at all coming, means one of the port was damaged, so it was not at all producing that output to that. So due to that, they found the machine was faulty. Then we just said that this machine is faulty because of this simulation and other thing. Then they changed the machine. Otherwise, this could damage the people, because initially it is supposed to produce more amount of heat and it should kill the good, means the cancer cells, but it is not killing it properly. So it is killing only the few amount of cells. The reason was this one. Then they recall that patient, and then they again treated that patient once again, and then they did that one. So those kind of things which was helpful if we are doing this reverse engineering and etc. And this is one type, okay, and so most of the time you can see that like we did, you can see that duration for this one, even for the clinical time is like 60 minutes it's taking, but you can see that ours is less than 10 minutes is taking for simulation, okay. So that therefore the doctors can take the decision, and not only that, so using this software they can change the parameters and they can play with many other parameters, and our software will provide a stochastic range between where to where you got to apply the heat and what type of things you got to do. Accordingly, the parameters also will suggest the doctor, so that they will change the clinical settings or they change the parameters accordingly. That will be helpful. This is one part of the software. The another part what we did is the next one, and this is the mathematical part, like the uncertainty quantification we did it, and then the optimization theory we did it using the inverse problem solving, and we tuned the parameters using the clinical environment. So this is one part of the clinical AI, and again summary of whatever I discussed for the radio frequency ablation, the same thing. So we've developed a past and patient specific RFA simulation which is running on a standard hardware. We don't require any high performance computing, etc. Just a simple normal setup which we have. Using that, only one GPU got extra we got. So most of the time we got in 5 minutes results, and you can refer this in my Nature Scientific Reports paper. So it is CPU accelerated one. Now the next one, we did another project called GoSmart project. Again, this is available, this website is available. You can just go to this two of this website, GoSmartProject.eu or smartmic.eu. Again, this is 5.4 million euros. Similar hospital, except in addition to that, there were few hospitals like Oxford University was part of us, and then the University Clinicum Frankfurt was also part of that. So this is another software. This is actually a web-based tool, where we developed a software where what we try to do is that in the previous one I was developing only radio frequency ablation. So here it will take care of many other cancers. We can do radio frequency ablation, we can do microwave ablation, we can do cryo ablation, and then we can do the IRE also. These four were our concentration on this project. Where so these are some of the idea about that, like RFA treatment, like it is a thermal, microwave is thermal, and cryo ablation usually they use it for the kidney. It's for the cold they use it, and IRE they don't use thermal, but they use the cathode and anode to treat that. And so in this RFA again, like it will take care of the heat sink, means that if there are some vessels present in the liver near the tumor, once we are inserting the needle, what is going to happen is that there will be a heat loss is going to come. That also we got to take care of it. So that heat sink tissue is very high in that RFA, so that needle will not be picking up the heat properly when the vessels are present. Whereas in microwave, in the quick period, it will reach the higher temperature, even 150 degrees Celsius it will reach. So in that case, this that whatever the vessel is presenting, it's not going to have significant effect. Still, it will be like low impact will be there, but it can do that. And like if there are vessels in the cryo, it will have some moderate impact will be there. And IRE there is nothing, but ablation size for RFA usually they take a small one. For microwave they take the larger one, and similarly the other comparisons I have provided here. And the RFA usually liver, and microwave liver and lung they use it, cryo for kidney and prostate, and IRE pancreas they use it. Again in this project, our software tool used to take care of all these images. So I'll just show you the website also. So here what I have is that I take the DICOM images, CT scan images, etc. we take it. MRI scan also here we take care of it. So the clinicians will provide this one. So it was the objective is that we want in this one the clinicians to come in forward and researchers to come forward, and then the developers, either the needle developers or the software developers or the algorithm developers to come forward, and then the power generator manufacturers and needle manufacturers to come forward, and the researchers who wants to study about the retrospective study or in vivo, etc. So those things they can come here and then they can put their models, they can put their data, and then they can simulate it. So I'll just show you the website. So here what we do is that we developed a website called CoSmart smartmic.eu, where the doctors can be anywhere. Okay, they can remotely monitor the work and they can do that. So here I can use that using a laptop, I can use it using a mobile phone, different types of mobile phone, and then you can use it using a desktop also. So in this one, this is called Anywhere Any Device. That is our logo for that. That's a motto for that, where the doctors can upload the images from anywhere. Okay, and they can upload the algorithm, they can upload the needle, everything, they can do it anywhere, and they can just visualize the treatment outcome, and then they can see like what is going to happen there. So here what we developed is that again, like we have developed Dockers, like if you some of you if you know like Google Colab, that provides the Python environment for free, where they use the environment like Docker and Kubernetes, where it will be deploying like for each one it will give its own Docker or Kubernetes, etc. Same thing here what we developed is that, so for each doctors or each model we deploy a Docker. That Docker is taking care of all these images where it will be uploading and modeling, and then you want to do simulation, etc. All this will be taken care, and the model parameters, tuning, everything will be taken care, and it will produce the output for you. Okay. So for example, so this is the software. Okay, this is the web-based tool. Okay, I will just show you the next image, which is showing the treatment. Yeah. So here what I have is, so I can upload the images. For example, I have upload some images. Okay, so I can upload pre-operative, post-operative, all the images I can upload. So for example, this is the pre-operative images I have uploaded. This is a CT scan images. Okay, similarly you can do the MRI also. In the segmentation, I have two types of tools I have. Suppose you want to use a polygonal tool to segment it, I can just create a polygon around that, then automatically it will segment that. Or there is a button here, so that if you just click it and then put in that wherever the liver is going to be there, you click it, then automatically that seed will take care of your liver segmentation. Similarly, if it is a tumor, I can just click it, or I can do that. Only vessel we couldn't do that, because vessel is a complicated structure where we did only semi-automatic segmentation, where at least you have to do the polygonal path you have to draw, so that it will give you the answers for you. So otherwise, remaining things we just put the click button. Okay, you just take a picture, you take that pen button and then put the pen on particular place, then automatically that will take care of the segmentation. So all these things will be automated. Only vessel is complicated, that's still under research, which we didn't do it in this one, but still we are doing that. So that it will take like little time, because the vessel structures are going to be complicated. And then we calculate safety margin, etc. And once I go to the simulation tab, I can use whatever type I want. For example, in the previous one I was doing only RFA. I have a similar type of lesion. Which type of treatment I should go for? Either I should go for RFA or microwave or cryo or IRE. All these things I can just simulate it and then see which one is giving better answer for me. Okay, so that we can do it in the simulation. So you just give that, there will be some tick marks will be there, you just check like which one you want, whether you want RFA or microwave, or you want combinations also, you can keep that. Okay, so those things we have did it in the simulation. Okay, so you just took the tick mark, automatically the digital twin will, our clinical AI tool will take care of that. And also we have developed something called validation, where suppose you already did the treatment and I want to compare two treatments, whether it is fine or not, or you already created a post ablation and you want to see whether these are matching or not. So those part is taken care in the validation part. So here we tested for each type at least 20 we tested. So in the previous one for liver cancer itself, RFA treatment we did for 100 patients we did it. Here for each one like RFA we did 20, microwave we did 20 and IRE cryo, each one we did 20 simulations. And so here the developers from various companies can come, and suppose the researcher who is good at RFA but they are not good at microwave, or they are good at some parameter estimation, all these people can come forward and then upload that and they can generate that. Okay. So this is available in this one, but there are some so this is like in Google Chrome you can use that. So these are the methods available, different types of methods. So Docker container, Elmer, Python we have used, and then we have used Microsoft SQL and Windows Server for the web server, and simulation, segmentation, everything is taken care here, image processing server. So there are some disadvantages that then we applied for another project to develop that. So here this is slower simulation. Okay, we are not using any GPU. In the previous one I used GPU, here I am not using any GPU, so therefore it is going to be a slower simulation, and data transfer is also going to be a little time consuming because I got to use the Docker containers, etc. The strength is like it is a web interface, anywhere they can use it, RFA, microwave, all these things you can do, and there are like opportunities are there. Okay, threats are mostly the security and maintenance is threats for that. So to overcome this, we wrote another project called SimCare, which I was when I joined IIT Tirupati, we started working on this. So I joined in IIT Tirupati in 2018. So at that time we started using we applied for this European funding, and then we got this one. So here the idea is that whatever I developed for the RFA as a GPU one, that I got to integrate here. Means I need to. So the main motive is that we already developed that, so we didn't apply much funding, we just applied only some 71,000 euros we applied. Our idea is to integrate that GPU, whatever I developed that, to be deployable in the web-based interface also. So that is the motive of this project, where again the same software, okay, but we just changed that to little bit different, where we accelerated RFA solver and microwave solvers mostly. So where we use similar to the clinic impact project, whatever I generated, I got applied here. And microwave solvers again I generated using vector Helmholtz equation and bioheat equation. So this part I accelerated using the GPU part once again, using the NVIDIA GPU cards. Then we tested this also once again, okay, where we had the testing for microwave also, we tested it and solved it. So we integrated in this way, same thing. The advantage is that, so here I am not using Docker or Ubuntu servers, instead of that I am just directly putting it in the GPU. So we are doing the GPU containerization here, and that will be taken care of that simulation. Okay, that is the main motive of this project. So here we developed a fast RFA solver. So for 40 minutes protocol, 2 minutes simulation time it takes, again in this web deployable also. And for microwave also we have developed a similar thing. For 60-minute protocol it takes 3 minutes simulation time. Okay, so during that time they can just do all these jobs. So this is like the only problem which we have is because it's web deployable. Suppose I have a data, uploading usually takes time because that's a large amount of data. So that is the major task it will be taking. The data transfer is the major bottleneck because it's not in the standalone computer, it is in the website. So depending on your bandwidth of the website, the data transfer will happen. So in that case, the data transfer is the major bottleneck. Suppose you are in a remote place where you are not connected, well connected with the internet, then this will take a long time. But remaining all like similar to that, the simulation time is reduced a lot here. Okay, that's the main motive of that. And so these are the mathematical models we have used, okay, which I have already told you. So in the interest of time, I just tell you the other mathematical model also, the cell death model which we developed with Oxford University. And the heat source model, usually what we have is that the needle also we got to imitate. So for that we used the Maxwell's equation, okay, Maxwell's equation used it for simulating that current and frequency which was simulated. With the help of some mathematical knowledge whatever I have, instead of solving one more problem of this Joule heat model, I developed a model called point source model, where you just insert the needle, around that the temperature where the needle is going to be there, it will be peak, whereas nearby places it's going to be less. So it is something similar to the normal distribution in the mathematics or statistics, they call it as Gaussian distribution. So that model I developed it, and then we have used it for solving it, and that also reduced a lot of amount of time for me, because if I solve for this one, again I got to wait for a long time, but instead of that I developed a Gaussian distribution model that takes less time. And not only that, this generator has some idea, like when the peak temperature is reached, automatically the power is shut off. Okay, so therefore it's the temperature dependent needle is there. So that is called as PID controller. That also we got taken care in our model, and then we developed it. Okay, and these are the, based on this we developed it. And last one, so this finite element, so this is the software I used mostly for this one, and currently we are using physics informed neural network also for solving this one, and FNO Fourier neural operator also we are using it. So here all the computations we did it in GPU, okay, the NVIDIA GPU we did it, okay. So this is the idea about that, and I'll just go to the next one, and then I'll stop it. So this is the tool which I developed, okay, basically this die score, how do we calculate it, etc., where we use the mathematical knowledge of how to calculate this volume of this with the surface only. We don't need to generate anything inside that, with the surface only we got to calculate that. So all this course I just optimized it, and then we developed it, and later some of the European hospitals also approached me for using that tool to use to check whether their die score and everything which they can compute it quickly. And based on this we did many simulations. I am just giving some 20 simulations data sets here, like how did we compare, what is the type of the protocol, like how many ablations they are doing, sometimes 1, sometimes 2, sometimes 3. So same thing, same cancer cells, but they got to do like, they got to take the needle and then put it again. So there are 3 and 4 will be there, and you can see the real duration like up to 62.9 also will be there. You can see the simulation in seconds, it's going to take only seconds, it's going to take, okay. So, and you can see that the die score and RVD, the relative volume difference, etc. Most of the things are like less than prescribed value by the consortium of one. And with this I'll stop. Actually I have a few more slides, like how the mathematical model we evolved and how does it came, okay. But with the interest of time I'll just stop it. If you have any questions, I'll be happy to answer. Yeah.
Thank you so much. Now the 60 lower questions.
Good afternoon, sir. I'm Dr. Nature from Central University. It is relevant to mathematics in clinical AI. It is very good. But I have a small doubt. You used in the bio-heat equation to convert into cell death model.
Yeah.
So generally we are using in the similarity transform technique, converting PDE to ODE. So is there any AI tool usage in that?
We don't need to, here we are not transforming that using similarity transform to ODE, we are solving the PDE itself directly, because nowadays these tools like physics informed neural network, that takes care of all this PDE itself directly. So in that case we don't need to go for the reduction of that. The training time for that is taking little time, but once we train the data, train the model for the prediction and all, it's going to take less time. So in that case, people are working on the physics informed neural network with the help of GPU computing, etc. So that model reduction we are not doing here.
Okay. So both equations are using to that?
Yes.
Okay. Thank you.
It is a wonderful talk. My first question is that are you using any random parameters in Penn's bio-heat model?
No, we are not using any random parameters. All the parameters, for example, whatever parameters we have developed is like the density of the liver, density of the tumor, density of the blood, everything we take from the patient itself. Okay, some of the parameters we take it, suppose we don't know a priori like some of the things, we know like range of parameters which we do it. That's why I call it as a stochastic discrimination. We simulate like within that parameter, within that acceptable range, we simulate it and then do. The major thing which we make stochastic is on the blood perfusion value. So sometimes when the treatment is happening, the patient will be nervous, although he may not be a high BP patient. Because of the patient is nervous, sometimes the BP, the blood rate will go a little high. So in that case, we simulated that range. So we have high perfusion, low perfusion, and middle perfusion is there. So based on that, all these three parameters also we simulate it and then see like what is going to happen.
But once you have fixed that domain or the range of the parameters, then there may be a situation where the equation has no solution.
In this case, it doesn't, because we always take that parameters which is going to be in the reliable range only.
Yeah. So that's why you are calling it as the stochastic.
Yes.
But there is no controlling parameter in that.
Here the controlling parameter is how to control that heat distribution, means heat generation from the needle, how to control that, whether we have to stop it at this location or we have to proceed further, that we control it. So that we give it to the doctors.
And the second question is that what kind of fast solvers you are using?
Fast solver is everything from the scratch we develop, using C++ we developed it. Currently we are using the physics informed neural network where we use the PyTorch etc. for simulating it. But during that time, only most of the time what we did is, I developed a C++ environment to simulate everything from the scratch.
No, I meant to ask the numerical, means are you using
Finite element method.
finite element?
Yes.
Are they multi-grid or?
It's multi-grid, yeah.
So, there is no data training, that part is there, like.
So the data training currently we are doing it. In this one what we did is the data whatever they provide, for this we were trying to use the, not the images we are not training, images are fixed for me, only the data which is corresponding to all these parameters which we are training it. But right now what we are trying to do is that, right now we are trying to take multiple, because we have 100 images from one and another 100 images from another one. So both the things we are trying to train together and then see like whether we can make some more optimization in this one.
So those parameters are so many, right? So
Yes.
Data, amount of data, how are you to do that also? You need a lot of data.
Yes.
So how are you managing that?
So currently we are dealing with these 200 data sets only. So using that we are just tuning it and then we are just making like different types of things, because our output is fixed for us. We know already the lesion, because this is retrospective one which for the pins which we are doing. During this one we were doing like in vivo. They simulated on bar and then they checked it. But now we are doing retrospective study. So we have already output known to us and we have a data synthetically generated because of our previous project where we have plenty of data generated. So that also we are trying to use it.
One quick information. I know that after the session we'll go for lunch. After the lunch we'll have the hands-on training session. Somehow we are able to pull up an industry biopack. So they are here. The CEO of Biopack Finlay is also here. So the session. Right, the way yesterday you were split into two groups and then you had an interaction, right? So today, first session will be joint